Hello guys, welcome to this video. So in this video I'll be discussing path integral formulation of quantum mechanics. Now I have already done a video on this topic in my YouTube channel. You can check it out. I will be giving the link in the description as well. I mean, you should check that out because in that video I have rigorously derived path integrals. I've rigorously introduced the concept of path integrals as well as mathematically showed how the path integral expression for the path integral as well as the free particle propagator is derived. I have also shown how the time independent Schrodinger equation for a free particle, I mean not time independent Schrodinger equation, I should say Schrodinger equation for a free particle for the potential when the potential energy is zero. I have also derived that and many more like standard results in quantum mechanics like de Broglie relation as well as Planck-Einstein relation in that video. I mean that video is a very introduction to path integrals for layman, like college students, undergraduate students with basic knowledge of physics should be able to follow. Path integral is typically not a topic that is taught at undergraduate level. It's a bit advanced, but yeah, you should definitely follow that video. Now in this PDF that you are seeing, the 72-page long PDF, this is actually it is not exactly my undergraduate dissertation, but it has been prepared from that document. I mean much of it is the same, to be honest. And so this is my undergraduate dissertation project. As part of my dissertation in my college undergraduate for my college undergraduate course, I explored path integral formulation under the supervision of my professor, Dr. Tanay Bhattacharya. Yeah. So now, of course, I'll not be telling you everything. I mean, this is not just I'll not be telling you what I did and what I did not do in that project, but this video is actually supposed to be a continuation of my previous path integral video. In my previous video, I did not cover some topics like a path integral for a particle with a non-zero potential. I did not cover all those topics. In this video, I'll be covering those as well. So it's kind of a continuation. You should definitely, like, if you're seriously interested in learning path integrals at an elementary level, at an advanced level, well, even I don't know, but if you're interested in learning path integrals at an elementary level, I think you should check that video first. Because in this video, I'll be starting from where we left off in that video. I'll not be going through the entire thing. Because that video is itself 4 hours long, of course, so you can understand the depth and the complexity of the topic. Like you can see, in that video, we discussed some basic ideas related to the, this kernel, classical, I mean, first of all, what is the motivation behind path integrals? So we know that, okay, let's just skip all this index. Let's come straight here. So this is just a history of quantum mechanics. I mean, not a comprehensive history, just a few lines, to be honest. Now this Schrodinger equation and the canonical quantum mechanics, what we're usually taught at UG level, at undergraduate level. Canonical quantum mechanics is mainly concerned with finding energy levels of a system. That is one important problem. I'm not saying canonical quantum mechanics is only about this problem, but this is a central problem in canonical quantum mechanics. Right? You solve Schrodinger's equation for hydrogen atom and all. Now the point is, this entire formulation, canonical formulation, is based on the Hamiltonian. You see, even in Schrodinger's equation, you see this is this thing right over here. It's called it's actually the energy operator. I mean this psi t. It's actually the wave function of the system. So wave function is basically a function, abstract mathematical complex quantity in quantum mechanics, which is supposed to, which contains all the information about the particle. And it has no physical meaning by itself, but the square of the modulus of the wave function gives you the probability of finding the particle. Now this is very vague. I will exactly tell you mathematically what I mean by that, because this statement by itself makes no sense. I know that, and we should not be using statements like, okay, the square of the modulus of psi gives you the probability. I mean, what is psi? What probability are we talking about? What do you even mean by probability? So you should define this rigorously. Whenever you're making a statement, you should be rigorous about it. But yeah, for now you see this notation. We have written psi as a function of time inside this this is called the bracket notation. This is actually a ket vector. Ket vector is kind of a special vector which represents the state of a quantum system in a Hilbert space, which is a special type of vector space. This entire canonical formulation is based on vector spaces and matrices and eigenvalues and eigenvectors. This is again mathematics. I'll not go deep into that here. Because this video is about the path integral formulation, not the canonical formulation. But yeah, that is the basic idea. You have a matrix and you can find its eigenvalues and eigenvectors, and you can represent the state of a system, and you can represent a quantum system, the state of a quantum system, as a column vector. So if you're in 3 dimensions, it will be actually, see, it's not it's very difficult to say it like this, but just to give a very basic idea, you can represent the state of the quantum system as a column vector, and you can represent a quantum operator as a Hermitian matrix, square matrix, and it has to be Hermitian. Why it has to be Hermitian? Because whenever you're performing a measurement, you must get a real value. Suppose you're measuring the velocity of a particle, you cannot get a value like 3 plus 2i. Complex quantity, of course, the mathematics of quantum mechanics defines this wave function, allows the wave function psi to be a complex quantity, but real measurement outcomes must be real. So keeping all this in mind, the mathematics demands that these matrices in quantum that represent quantum operators must be Hermitian matrix. So essentially, you are multiplying a square matrix with a column matrix of the same order, of course, and then the result will also be a new column matrix, and this is the new state of the system. Now, this multiplying a state with a operator matrix is not exactly the same as performing a physical measurement, but in canonical formulation, what we usually do is we measure the eigenvalues and eigenvectors of this operator matrix, and see, suppose for instance, if you have a 3 by 3 square matrix, then there are 3 possible eigenvalues, right? Now they may be unique, they may be distinct eigenvalues, they may be there are many possible cases, but anyway, so these 3 eigenvalues, they correspond to the possibilities. I mean, suppose this operator is let's say for instance it's a momentum operator, so you're measuring the momentum. So these 3 values correspond to the 3 possible momentums. I mean, this is just a very simplified scenario. In a real system, if you perform a measurement, there are usually there are many possibilities, often infinite number of possibilities, not just 3 possibilities. But let's say so these 3 eigenvalues will correspond to the 3 possibilities. So wherever you're performing a momentum measurement, in this simplified example, you are sure that you will get either possibility 1 or possibility 2 or possibility 3, and corresponding to each eigenvalue you can find an eigenvector. This is simple linear algebra. Doing that, you can each eigenvector will give you the final state. Eigenvector is basically a column matrix, right? Like a column matrix. Okay, so that will give you the final state of the system corresponding to that eigenvalue. So like this, you will get 3 possible final states corresponding to 3 possibilities. So now if I ask you, so okay, you have 3 possible values of momentum measurement. So what is the probability that you get possibility 1? What is the probability that you get possibility 2? And what is the probability that you get possibility 3? So for the probability that you get possibility 1, you take the inner product of the initial state and the final state. Final state is just the eigenvector, and then you take the square of its modulus. So this is how it's defined. Now the point is, like I said, one of the central central problem we deal with in canonical quantum mechanics is finding energy levels of systems, atoms, and so on. So in this equation, this corresponds to the energy operator, whatever, and yeah. But this thing in square brackets, as you can see, this is actually the Hamiltonian of the system. So for a conservative system, we know that the Hamiltonian is equal to the total energy. So here this V is the potential energy, and this corresponds to the kinetic energy, because it's easy to understand, because see, Schrodinger's equation cannot be derived. It's kind of a postulate of canonical quantum mechanics. You can show that this equation holds true for some specific cases, but you cannot derive this equation from first principles. But yeah, this quantity right over it corresponds to the kinetic energy operator. You can understand it like, just to give a very qualitative basic intuition about it. Kinetic energy is p squared over 2m, right? In classical expression for kinetic energy. So p is the momentum, and p we know is h cut square k square, or h bar squared k square. So you see, we have a h bar square here, k square. You can think of it that k, what is k? What is k? K is the wave number, right? So k is kind of, if you think about it, k was 2 pi over lambda. So 2 pi is a dimensionless constant, but lambda is, the unit of lambda is the unit of x. It's a distance. So k squared, the dimension will be 1 over x squared, right? And you see, we have a 1 over x squared here. I'm just showing you the dimensional analysis, nothing more. So this is not just a differential operator, no dimension, but here we have a x squared and 2m. So p squared over 2m. Actually, you see this negative, I del x is the momentum operator. So if you have p cap squared over 2m, p cap is the momentum operator. In place of p cap, you can write I del x. So if you square it, it will be I squared will be -1. We have a negative, and this will be del square del x square. Now I cannot show you exactly explain why the momentum operator is I del x and all those stuff in this video. But yeah, so basically this is the Hamiltonian, kinetic energy plus V, potential energy. So now the primary motivation behind path integral formulation of quantum mechanics is that, So we already have a quantum mechanics, the Schrodinger's canonical quantum mechanics, that is based on the Hamiltonian. And in classical mechanics, we have two like equivalent formulations. One is the Hamiltonian formulation, one is the Lagrangian formulation. So in Newton's mechanics, like Newton's laws and all, where we primarily deal with the force, like F equals ma. I mean m d square x over dt square. Acceleration is d square x over dt square equals to the force. So this is the primary equation we deal with in Newton's mechanics. I mean Newton's mechanics is mostly interested with the force. But when we have many particles and more complicated systems, then it often becomes difficult to directly calculate the force. So then we have more general formulations of classical physics like Lagrangian and Hamiltonian. So it's, for instance, in Lagrangian we talk about generalized coordinates and the degrees of freedom, like we define it in a different way, and we have something called the Euler-Lagrange equation, which is the equation looks more difficult, more complicated than Newton's F equals ma, but for complex systems it's much more easier to use this equation. They will give you the same results, of course. So now the motivation is that, okay, so in classical physics we have two equivalent formulations, Lagrangian and Hamiltonian, and we have already a quantum physics which is mainly based on Hamiltonian. So then is it not possible to create an alternative formulation of quantum mechanics based on the Lagrangian? This was the starting point, and yeah, indeed, like path integral formulation is based on the Lagrangian. So in classical mechanics, the Lagrangian formulation, first of all we define the Lagrange of a system, which is L, which is T minus V, the kinetic energy minus the potential energy of the system. And this action, this is the most important, plays the most important role in the Lagrangian formulation of classical mechanics. It's defined as the time integral of the Lagrangian. This is the action S. It's the time integral of the Lagrangian. Suppose we are studying the evolution of the system between time t naught to t. So we take the time integral with the limits t naught and t. And so this action basically describes the trajectory of the particle in evolving from initial state to the final state. Now in classical physics, the particle will always follow the path with the least action when the action is minimum. We can assign a single trajectory to the particle, and this path is called the classical path. But we cannot do the same in quantum mechanics because in quantum mechanics, you see, there are like many possible paths. This is the classical path. Okay, so this figure, you see, in quantum, like in classical mechanics, it's we can define a unique trajectory. We can assign a unique trajectory to the particle. Say the particle is evolving from state A to state B. This is the x-axis, which is the position axis, and this is the time axis. So this A for xa comma t, it's the initial state of the system, is the final state of the system. So in classical mechanics, we have a single unique classical path. I mean, of course, if you throw a ball and use Newton's laws or whatever in classical physics, you can actually predict the exact trajectory of the ball. If you throw the ball in exactly under the same conditions sometime later, you will not expect the ball to follow a different trajectory. But in quantum mechanics, due to a lot of factors in quantum mechanics, you cannot define an exact trajectory to the particle. You know, it will vary between, like you are only allowed to ask the question like, what's the probability that the particle will follow this path, what is the probability that the particle will follow this path, and this kind of questions. But you cannot say that the particle will always follow this path. Maybe if you under the same conditions, sometime later the particle will follow this path. Of course, there is a random probabilistic element in quantum mechanics. Now see, that is what path integral does. Path integral basically it kind of sums up the contribution from all possible paths between a fixed initial point and a fixed final point, and this is what we call the sum over paths or path integrals. Path integral. Now you may ask the question, like in quantum mechanics we know that due to uncertainty principle, it's impossible to exactly accurately pinpoint the position of a particle at any point in time. But we said that this point A and point B, they are fixed points, the initial and final points. So now you may ask, how can we pinpoint? I mean, how can we exactly say that the particle is in point A? The initial point is exactly this point A, because for point A corresponds to a unique value of position and time. That means we are saying that at time ta, we are 100% certain that the position of the particle is xa. But that's technically not possible if you take into account the uncertainty principle in quantum mechanics. But see, actually the reason is, this is a very good question, but this question is often not properly explained or properly properly outlined in path integral materials. That is that this is just a theoretical model. We are not saying that the particle is exactly at point A when it's starting. First of all, whatever we're doing right now, it's a very simplified scenario. We're doing in Euclidean space. In real life, when we apply path integral to more complicated, like actual in quantum field theory and all, it's not so simple. Second of all, we are saying that if the initial point is A and if the final point is B, then what is the total sum over paths? Understand the target question very clearly. Our target question is, if the initial state of the particle is A and the final state is B, then what is the sum over paths? Like, we are not saying that the initial state is A. We are not making a claim. The initial state can be anything. We cannot like determine it. We cannot predict it. There will be some uncertainty. But yeah, at a point, at one particular point of time, the particle will be at some position. We cannot determine exactly what position, but it will be at some position. Maybe it will be at a different position in the next instant of time. So say we have just taken a snapshot of the particle when it is at position xa and time ta. We are not generalizing the claim that the particle will be at position xa in time t. But yeah, for this particular starting point, and we have just in our imagination we have defined an end point. Now we are asking the question, like, for this particular initial state, and if we choose that to be the final state, then what is the probability and what is the sum over paths? So if you understand the target question clearly, then this is actually no paradox at all. Now these things we will very briefly discuss a double slit experiment as well. After that, we'll move to path integrals for particles with potential, with non-zero potential, because otherwise everything else we've already discussed in that previous video. So yeah, this is one of the best ways to start learning about quantum mechanics. In Feynman lectures on physics, volume 3, the volume on quantum mechanics. This is the way Feynman introduces us to the subject. He starts with this double slit experiment with electrons. So this experiment has been done by Thomas Young with light, and he observed that when we shine light through a screen with two parallel slits, we get an interference pattern on the final screen. And this is only possible if light has a wave nature. Okay, because see, if light was a particle, for instance, if these were particles, this is what we would have expected. Here is a slit 1, here is a slit 2, so the particles are passing through the two slits. So yeah, the maximum most number of particles should be found directly behind the slits. Maybe some particles may touch the edges, get deflected slightly because they arrive at an angle and then they might get deflected, but you would expect this kind of distribution. Most of the particles will be found directly behind the two slits. But if we find an interference pattern, then that means these are not really particles. They must have a wave nature, because if they have a wave nature, then see here you can think of it like this. Here we have a wave and here also we have a wave. So both the waves will interfere, and when waves interfere, we have alternate regions of maxima and minima. So this is the maxima. Maxima means there is some probability of finding the electrons here. Some of the electrons end up at this position in the final screen, but this is the minima. No electrons will end up at this position, and this kind of interference pattern. You see, this is the usually what we expect if electrons were indeed particles. But this is what we observe, kind of an interference pattern. That means the electrons are not particles. They are wave. They have a wave nature. Right. This is very important. Now, and this was one of the very good indications we got that particles or matter also has a wave nature. And that means, what does that mean actually? That means it's like, how to put it? Yeah, this is actually the very basic postulates of quantum mechanics, like de Broglie relation. It's all about wave-particle duality, de Broglie hypothesis. And then, since matter has a wave nature, you can think of it like this. If a particle has a wave nature, that means you cannot pinpoint the position of the particle. The particle will, it's kind of spread out like a wave. So, you see, here also I have actually shown you Feynman's alternative statement. Before that, you see here, let me just quickly go through this. This is a different document, but anyway. You see, according to Louis de Broglie's hypothesis, matter has a wave nature. Every particle has a wave associated with it that is spread out over some distance. This can be roughly linked to the idea in quantum mechanics that particles have a probability of existing at more than one position before they are observed, or in other words, before a measurement of their position is carried out. So we often say that in quantum mechanics, before we measure the position of a particle, they can be at multiple positions at the same time. Now, it's not entirely correct to put it that way. It's more correct to say that before we perform a measurement, you cannot determine the position of a particle. So it has a probability of existing at multiple positions at the same time. It has a probability of existing. That is a more correct terminology, I think. And this is technically called the superposition principle or quantum superposition. Of course, after the measurement, we will always find the particle at some definite location. But if we measure it again under the same conditions, we may find the particle at a different location. And this is why there is some uncertainty. And yeah, of course, like this is not due to any experimental error or any kind of any error on our part. This is like even in principle, even in theory, we cannot know the precise location of a particle. This is a kind of an inherent property of the universe. Now the uncertainty principle is a you can think of it, it's a consequence of the fact that the wave function describing a particle is not a localized wave, but rather a superposition of waves. So like I said, the particle has a probability of existing at many different positions, and so you have to superpose all of these waves, right? And since we're talking about linear systems, I mean linear algebra and all, this superposition is allowed. In quantum mechanics, the wave function of a system essentially contains all the information that can be known about the system. However, by itself, the wave function has no physical meaning. The square of the modulus of the wave function can be interpreted as some probability. Now here I'll tell you exactly what this means. So the wave function of a particle roughly translates to the amplitude of the quantum mechanical wave describing a particle. We say there is a wave associated with every particle. So the amplitude of the wave is directly correlated with the wave function. And the wave function is of course a complex quantity, and it's a function of both position and time in general. And of course it's just an amplitude of a wave, so it can rise above the x-axis or below the x-axis, so it can take on both positive and negative values. But since probability is always a real and positive quantity, a real physical probability, it must lie between 0 and 1, right? So that's why we interpret the square of the modulus as the probability of finding the particle at some given position at some given point in time. Now we do not usually speak about finding a particle at a specific point in space-time because of, again, it's not possible to like exactly pinpoint a precise location due to the uncertainty principle. So a more meaningful question to ask would be, what is the probability of finding this particle within the region in space between x to x plus dx? A very small region in space. See, dx is an infinitesimal amount, but yeah, it's still a finite region in space. Now, so if psi is the wave function that describes the particle at position x and time t, psi is a function of x and t. So here we have assumed a one-dimensional space for simplicity, or you can write psi x, y, z, t, whatever. Then the answer to the question, like what's the probability of finding the particle between x to x plus dx, would be mod psi squared dx. So in that sense, mod psi square is not really the probability, it's rather the probability density. Mod psi square is what? It is the, this is the probability, this entire thing. Mod psi square dx is the probability of finding the particle between x to x plus dx. So if you divide this entire probability by dx, then you are left with mod psi square. Dx will just cancel in the numerator and denominator. That's why mod psi square is kind of the probability density. So yeah, and the uncertainty principle states that yeah, if you, this delta x is the uncertainty in position measurements. So suppose you're measuring the position of particle, there will be some uncertainty, and this is the uncertainty in the measurement of the momentum of the particle in the same direction. That's why we have written delta px. So the product of both these uncertainties must be greater than a non-zero constant. This is reduced Planck's constant, h bar. That means you cannot know the position or the momentum precisely, because if you know the positions precisely exactly, that means the uncertainty or the error in your measurement is 0. But if delta x or delta px, even if any one of them is 0, that means this inequality will not hold, right? Because this has to be greater than a positive constant. It's not allowed to be 0. That means there will always be some uncertainty. And you can think of it even like I mean kind of qualitatively, like if you want to measure a position of an electron, so you need to shine light on it to exactly be able to determine the position. And light is a form of energy, right? So light contains photons, so the photons will collide with the electrons, and the electron will be scattered, maybe in some different direction. So there will be a change in the velocity of the electron because the direction is also changing, and that's why there will be a change in the momentum. So if you want to measure the position of the electron, you are disturbing its momentum. And if you want to measure the position very accurately, you need to shine a light of very high energy, because high energy means low wavelength, and lower the wavelength of the light, more accurately you can measure the position, exact position. But on the other hand, higher energy light means the scattering will be more, and the uncertainty in momentum will be even more. Technically, if delta x tends to 0, then delta px should tend to infinite, right? Then the uncertainty in momentum will be almost infinite, which means which is not physically allowed, because that means the particle, you cannot that makes no sense physically. If the uncertainty in momentum is infinite, the particle is allowed to take on any value of momentum. It will be entirely random. And same for the position. You can also, there is also an alternate uncertainty relation between energy and time. Basically, these are all canonically conjugate variables. Like in Fourier transform, we have seen that time and frequency inverse are canonically conjugate. They are Fourier transforms of one another. And frequency is basically energy. In quantum mechanics, energy is just frequency multiplied by a constant. So they are just positively correlated. And that constant is Planck's constant, E equals h nu, right? Similarly here, delta x, delta px, you see what is p momentum in quantum mechanics. You can see momentum is h bar over h bar into k. Now h bar is reduced Planck's constant, h over 2 pi, and k is 2 pi over lambda. So essentially momentum you can write h over lambda. I mean, of course we know that h over lambda is p from de Broglie's relation as well. So p is h over lambda, that means h is p lambda, right? And lambda is essentially corresponds to the position. So delta, in place of delta x you can think of it like lambda, and this is p and this is h. So you see dimensionally it's the same thing, h and it's p into lambda. You can understand it in many different ways actually. Okay, now we discussed this very briefly, the double slit experiment with electrons. Now I will discuss the Feynman gave an alternate statement of the uncertainty principle. That's why I discussed the uncertainty principle once again with you. I think I've done the uncertainty principle in many of my previous videos as well, but yeah, never mind. So it's like the important point is that this is how Feynman defined the uncertainty principle. I mean, Feynman stated the uncertainty principle. See, Richard Feynman stated the uncertainty principle in an alternative and arguably more general form. Any determination of the alternative taken by a process capable of following more than one alternative destroys the interference between alternatives. That sounds a little bit technical, I know, and it's kind of confusing. The wording, the phrasing is maybe a bit confusing. Too much use of the term alternative, but whatever. See, basically what Feynman is saying, in this case, the electrons can take many possible paths from the initial point to the final point on the screen. Many possible paths through the two slits, of course. So usually we get this interference pattern, but if we try to measure, if you try to determine whether the electron passed through slit A or slit B, slit 1 or slit 2, then it is observed that this interference pattern is destroyed, and then we get back what we expect classically. And mathematically this means that, see, this is the probability P1, this is the probability P2. P1 is basically the mod square of the wave function psi, corresponding to the case when the electron passes through slit 1. And similarly P2 is mod psi 2 mod square, where psi 2 is the probability amplitude corresponding to the case when the electron passes through slit 2. So if we try to measure whether the electron passed through slit 1 or slit 2, then the interference pattern is destroyed, and then the probability is simply given by what we classically expect, the sum of the two probabilities, P1 plus P2 mod psi 1 mod square psi 1 plus mod square psi 2. But if we don't try to if we don't try to perform an intermediate measurement, in other words, if we let the electron evolve as it is without disturbing it in the middle, then the interference pattern is not destroyed, and then the total probability is given by psi 1 plus psi 2 mod whole square. See, there's a difference. This is actually the superposition principle. Superposition principle says that you can add up the amplitudes of the waves, superpose the waves basically. So here first of all we add psi 1 and psi 2, the probability amplitudes, then we take the square of the modulus of this entire psi 1 plus psi 2. But here when the superposition principle is no longer true, then we first consider the individual probability for case 1 and then the individual probability for case 2, and then we add the probabilities. So this is an addition of probability and this is an addition of amplitudes. Okay, now Feynman says that any determination of the alternative taken by a process capable of following more than one alternative destroys the interference between alternatives. So we will qualitatively try to understand why this is equivalent to the uncertainty principle, Heisenberg's uncertainty principle. Because see, first of all, if you try to measure whether the electron passed through slit A or slit B, that means you have to put some detectors here. So say you put a detector of light, you put some light here and you put some light here. So your idea is if the electron passes through slit 2, then there will be some scattering here. That means I can understand, okay, the electron passed through slit 2. And of course we will be using light such that scattering here will not extend up to slit 1, because then you cannot determine it uniquely. But the point is, if there is a scattering, then you are actually disturbing the path of the electron. Then you are kind of introducing some uncertainty in the path of the electron, and that means you are tampering with the interference pattern. Now Feynman proposed an alternate thought experiment. Now let's assume that this is the wall with the two slits. You see, here is the slit 1, is this slit 1 and this is slit 2. And Feynman assumed that, let's assume that this is just a thought experiment. Feynman said that let this slit be free to move vertically. You see, it's written motion free and there are some rollers. So that means this screen is not fixed. It can move, it's free to move vertically, up and down. So now let's say the electron passes through slit 1. Let's consider the case when the electron passes through slit 1 and it has to end up at this position in the final screen. I mean, it can end up anywhere, but we have put a detector here, so we are considering the case when the electron passes through slit 1 and ends up at this position in the final screen. That means the electron has to first of all it will have to reach slit 1. Now from slit 1 it must deflect downwards to reach this position. So as the electron deflects downwards, there will be a recoil momentum, and this wall, since it's free to move vertically, it will be deflected upward. So this is for case 1. Let's say PB. In this case, the moment of the electron is PB in this direction. Now see, this is due to conservation of momentum, of course. Now in this case, and when the electron has to pass through slit 2 and reach this position, it will have to deflect upward. That means the recoil momentum on this wall will be downward, so the wall will move downward. So then in that case, let's say it's PA. So the point is, this delta px is the difference in momentum in both these cases. It can be measured because the wall is free to move, and you can suppose you have some reference point. Suppose you have put an origin here, so you measure the initial position of 1 and 2, and then thus this wall deflects upward or downward, so you can measure the difference, right? And then you can measure the time it took to cover the distance, and then you can measure the velocity, and if you know the velocity, you know the momentum. So technically, without disturbing the electrons, see here you are not placing any light here, you are not placing light and scattering the electrons, you are not disturbing the path of the electron, but even without disturbing the electrons, you can actually measure delta px. But uncertainty principle says that if you know delta px, then you cannot know delta x, and this is true. You see why? So since we know delta px accurately, we cannot measure the exact position of the slit screen, and as a result the difference in the exact positions of the slit delta x with sufficient accuracy. Now we assume that we know the initial position of 1 and 2, otherwise we cannot know the momentum. But we are trying to show that Feynman's statement is equivalent to the uncertainty principle. It is equivalent to Heisenberg's del x del px greater than or equal to h pi over 2. So to show that, we assume that Heisenberg was right, and we show that why what Feynman said must be true if delta x delta px has to be greater than a non-zero constant. So if delta x delta px is greater than a non-zero constant, that means in this case, since we know delta px, then we cannot know delta x. That means the position of the slit is uncertain for various measurements, for various electrons. So since the position is uncertain, we cannot, as a result, we cannot pinpoint the position of the electron on the final screen as well. And that means we are essentially destroying the interference pattern, because if you cannot know the position of the electrons for all the throws, you cannot you cannot get an interference pattern. You're disturbing the system, and this is what Feynman said actually. If you see the statement, any determination of the alternative taken by a process capable of following more than one alternative destroys the interference between alternatives. So why this and this are equivalent? I think I gave you a very rough qualitative idea. Okay, so now in the path integral formulation, we have already discussed in that previous video how the kernel is defined. So basically it's nothing. You see, the kernel from A to B, from initial point A to final point B, we define it as the sum over paths. So this is the contribution from each path, the exponential Euler's number E, so e to the I s over h bar. So s is the action for that particular path, that's why we have written summation j e to the I s j over h bar. So suppose 0, 1, they are all numbers of the path. 0 corresponds to the classical path with the least action. So that means we have each path has a contribution, but this contribution depends on the action of the path. Every path will contribute e to the I s over h bar, where s is the action of that path. So we sum over all this contribution, and this a is just a normalizing constant, normalizing factor. That is the basic idea. Now all this I'll be skipping here. Okay, I've already discussed this in previous videos. See, this is the multiplicative law of propagators, very important. This actually links back to this. Let me just quickly discuss this once more, even though I've discussed this in the previous video as well. This links back to the superposition principle in canonical quantum mechanics. Give me a second. Yeah, this is so we can define the kernel B comma A, which is the kernel from A to B, as the sum over all the paths connecting A to B directly. That's what we can define. But we can also define the kernel from A to B by considering an arbitrary intermediate point C. This is a fixed point, but arbitrarily chosen. It can be any point between A and B. The exact point you choose it arbitrarily. Okay, so then you consider all the possible paths from A to C. That means you consider the kernel from A to C. Kernel is basically the sum over paths or propagator. These are terminologies we use in path integral. Basically, when I say kernel A to B, that means I'm talking about all the sum over all the paths from A to B. So yeah, in this case, you multiply the kernel from A to C with the kernel from C to B, and then you see here I've also shown you the exact mathematical derivation. But again, this is not required. I mean, I'll not be covering it right now, but yeah, this is the multiplicators of propagators. Kernel from A to C, this is the kernel from A to C, and this is the kernel from C to B. So you multiply them and then you integrate over dxc. I mean, you integrate over all possible values of xc. Because this initial value of xc, this was arbitrarily chosen. I mean, I could have chosen a different xc. So to make sure that you take into account all the possible values of A and B, because ultimately you're trying to define the kernel from A to B. So to ensure that you have to you have to take into account you have to integrate over all these possible values. Now this is the multiplicators of propagators, but you see this is actually equivalent if I this is in continuum basis, because we are talking about an integration here, so it's in continuum basis. But in discrete basis, if you replace the integration with summation, then this is the same as the superposition principle. You see, the above equation is similar to the expression of the superposition principle in quantum mechanics. This is the superposition principle. So here BA, this is how we write inner product. Now in canonical formulation of quantum mechanics, we cannot talk about kernel. Kernel is something we talk about in the path integral formulation. So this means the inner, mathematically this is the inner product between A and B, and physically this is the probability amplitude of the particle evolving from state A to state B. So it's kind of the same as the kernel. The kernel is also a kind of a probability amplitude. K B comma A is the probability amplitude from A to B. So this is also a probability amplitude. So you can see the equivalence of the left hand sides of both these equations. Now here we have an integration over all possible values of xc. Here we have an integration over all possible values of some intermediate observable c. And here we have kbc. This is the probability amplitude from c to b. And see, we have here c to, this an inner product between c to b. And kca, we also have this a to c. So both these equations are actually equivalent, and this is how we define the superposition principle in classical, I mean in canonical quantum mechanics. So basically here we see that when this a to b probability amplitude, what this actually means is that, let us assume that A is a position and B is momentum, suppose. So this actually means what is the probability amplitude. Let me put it differently. This is the probability amplitude. So that means if I take the modulus square, if I take mod square of this quantity, inner product of A and B, that will be the probability. Now probability of what? The answer to that question is, if you perform a measurement on the observable A, which is, for example, let's say a position observable, then suppose you get a value of position A. So this is the new state of the system, position A. Once you perform a position measurement, the state of the system becomes that position state. Now on this position state, you are performing a second measurement with a momentum observable B, and you are getting a momentum outcome B. So what is the probability that initially you perform a position measurement and you get position A, and then you perform a momentum measurement and you get momentum B? So what is the probability of that? The probability amplitude corresponding to that probability is actually given by this inner product of A and B. And you can this is mathematically equal to this thing. So basically here also what you are doing, you are considering the inner product of CB and AC over all possible values of C. Now what is C? You understand that A and B are two observables, two like kind of two measurements we are doing. A could be position, B could be momentum, both could be same, like both could be position measurements, whatever. But this C is something, C is also a quantum observable, but C is something which we are not doing any physical measurement. This is just a mathematical definition. This is mathematically equivalent to this, but we take any arbitrary observable with the same number of like the same spectrum size as A and B, of course, like A, that means I equals 1 to n, so the spectrum size of C is n, that means A and B must also have same spectrum size, but it is any arbitrary observable. There is nothing special about C. We are just taking C just to make the mathematics simple. We are not performing a physical measurement on C, and that's where the superposition principle holds. You see, in case of this, what do you call it, this double slit experiment, if we actually perform a physical measurement, we get this, that means the superposition is destroyed. But here we get this. The superposition principle holds. We are not performing any physical measurement on any intermediate observable C. We are only concerned with A and B. But yeah, mathematically the superposition principle we can write it over as a sum over some arbitrary observable C. Okay. And yeah, I already discussed all of this, right? Now, if in addition to the measurements on A cap and B cap, this is the notation for observable. When we're writing A cap and B cap, that means we're talking about the observables A and B. Now, if we also make a physical measurement on the intermediate observable C, then the superposition principle would no longer hold, as I already told you, and then the probability would be given by then the probability would be given by C summation mod square of this thing. So first we are like computing the square of the modulus of this thing, and then we are just taking the sum. But here, when the superposition principle holds, we first take the sum over this, and then we take the square of the modulus. Basically, this is like I already told you. This is the sum of. I'm sorry. Yeah, this is the sum of amplitudes, and then we are squaring the final resultant amplitude. The mod squaring the resultant amplitude, and this is the sum of probabilities. First, we are mod squaring to find the probabilities, and then we are taking the sum of the probabilities, like we would have done classically. And this is the free particle. For a free particle means zero potential. We have already discussed the free particle in that previous video. Okay, so how the free particle action is discretized and how we can arrive at the propagator of the free particle, which is I think, yeah, this expression right over here. And for simplicity, we have this time intervals tb minus ta. We have just written t in place of this. We have assumed the initial time to be 0 and the initial initial position to be 0 as well. So xp minus xa, just assume xa to be 0 and ta to be 0. So the initial point is the origin 0 comma 0. Then in place of tb you can just write t, and in place of xb you can just write x. But keep in mind that this x and t, they are intervals, time intervals and position intervals. They are not really just a single variable, single value of position or time. It appears that way, but it's you should like remember that. Now we did this simplification because to be able to plot this. So now essentially we are interested in plotting the real part of this thing. So this is the simplified expression for the free particle kernel, the probability amplitude of a free particle with zero potential from moving from A to B. Now we are interested in studying the behavior of this kernel as a function of position as well as time. Now to study the behavior, that means we are talking about the physical state of the system. So that means we should be dealing with real quantities. We should do away with all imaginary or all the imaginary part. So that means we have an under root I in the denominator. So we should multiply this kernel with under root I. So that's what we have done. So this gets rid of this, and we have e to the I something. That means this is a complex quantity, right? This is the polar form representation of a complex number. So we should take the real part of this entire thing as well. So this is what we'll be plotting. We'll not be directly plotting this. Okay. So if you plot this as a function of x position, then you get this kind of behavior. I've also shown you the code. This is a very pretty simple Python code. This is my output. You see it looks the same. This is my output, and this is taken from Feynman's book, Richard Feynman, Albert Hibbs, the famous book on path integrals. This figure is taken from, you see, Quantum Mechanics and Path Integrals by Richard Feynman, Albert Hibbs, and Daniel Steyer. And this is my plot, the output of my plot. So from here we can understand that, you see, this is the mean position of the particle. X is 0. Now this is negative values of x means the particle is moving in the opposite direction. Of course, position negative means that. So the particle can move either this way or this way. But the point is, you see, for greater values of x, I mean when the magnitude of x is increasing, either to the left or to the right, I mean for higher values of x, you see the wavelength is decreasing. Here the wavelength is more and the wavelength is decreasing. The farther we move, the wavelength is decreasing. You can understand it in the following way. This is actually from the de Broglie relation. H over p is lambda, right? So lambda, the wavelength, is inversely related to the momentum p. So here the wavelength is decreasing. That means the momentum should be increasing because they are inversely related. And of course, for a particle from its mean position, for a particle to reach great distances, it must have a very high value of momentum. Otherwise, it cannot reach reach very great distance. So it all fits it. And I have also discussed mathematically how you can derive the de Broglie, not exactly derivation, but how you can kind of show that de Broglie's relation holds using some very simple mathematical approximations and manipulations. I've also shown that in my previous video. I'll not discuss that here. But you see here, you can arrive at this equation. H over P equals lambda, or lambda into P is H. And so this is, we plotted this quantity, a real part of under root I into the kernel as a function of x. You can also do the same as a function of time. And the plot will look like this in this case. You see, I've also shown you the plot which I did in Python. Now it looks like this. We have plotted the same quantity, this real part of the free particle propagator, but now as a function of time. And this decaying amplitude, you can understand it in the following way. See, why this decaying amplitude? Because first of all, energy. Okay, before the decaying amplitude, look at this. Here the wavelength is very small. I mean, it's just like this. But as we are with increasing value of time, the wavelength is also like, increasing. Now energy E is proportional to frequency. E equals h nu, and frequency is inversely related to lambda. So that means energy is inversely proportional to lambda, right? E equals hc over lambda. So more the time, I mean, see, you can understand it like this. More time means what? Less frequency, because frequency is inversely related to time. Frequency is basically 1 by time period. I mean, the very classical idea of basic idea of frequency, it's inversely proportional to time. Frequency and time, they are canonically conjugate variables, right? So higher the time means lesser the frequency, and low frequency means low energy, which corresponds to a longer wavelength. But why this decaying nature? This is very important to understand. Now I just now told you that this t which we are using here, this t in this expression, basically, you see in this expression, I told you that for simplicity we assumed Tb minus Ta to be just simply T. Where is it? Yeah, here. Actually we have Tb minus Ta. Ta is the initial time, Tb is the final time. Now for simplicity we are writing T, but this T is actually a time interval. Yeah, numerically if we assume, if we take Ta to be 0, then numerically this is just, okay, Ta is 0, no matter, but this is actually a time interval, not a single point in time. So now if you think about this, since this is a time interval, so this means a higher value of t means a longer time interval. So you have fixed the initial position of the particle, that is A. You have also fixed a final position, that is B, final state. And this quantity, real part of the propagator is basically probability amplitude. So this quantity which we are plotting along the vertical axis is basically tells you something about the probability that the particle will actually reach the final state B from the initial state A, because this is the kernel from A to B. So this is basically probability. Now you have a particle that starts from A, and you have a very small time interval, and it has to reach B. So since the time interval is very small, the particle does not have a choice to deflect very much, or kind of, how to put it, the particle does not have a choice to behave very much randomly. Think about it like this. How to tell you? Give me 1 second. Okay, look at this picture. Ignore all these notations, epsilon, all these things are not required here. I've discussed this actually in the previous video. Now this is point A and this is point B. So suppose this is a very long path. Suppose that means the time interval t is very, very high, very big, very large. So in this case, the particle starting from A will have ample amount of opportunities to go somewhere else rather than reach at point B. But suppose if B was here, this is A and this is B, then also the particle could have maybe moved this way, that way, that way. But the probability is definitely much more that the particle starting from point A will end up at point B, since the particle is not getting enough time to explore the other alternatives. If the time interval is very small, if the initial and final states are very close together. So that means, look at this plot, for a very large value of time interval, the probability is decaying or decreasing, the probability amplitude is decaying because the probability is decreasing. The probability that the particle starting from A will exactly reach the final state B after a very long time interval is decaying, is less. But for relatively small time intervals, we see we have a higher probability amplitude. That is the interpretation of this plot, the visual interpretation. And you can again from here also you can show this Planck-Einstein relation, E equals h nu. I have discussed this also in the previous video. I will not be running you through the derivation in this video, of course. Yeah, now this is very important. Particles with non-zero potential energies. So now we'll be studying a particle that has a potential energy which varies with position. See, for simplicity, we are not considering a potential that also varies with time. We are considering a potential that only varies with position. So The potential is different at different points in space, but there is no time variation. I mean, at a particular point in space, the potential remains the same over time. That is what we're assuming, just for simplicity. So now in this case, the action will be a time integral ta to tb, time integral of the Lagrangian t minus v, and here we, in place of v, we cannot write 0 because we are not talking about a free particle. Now we're talking about a particle with a non-zero potential energy. So there are basically two very important potentials which we'll be discussing. One is the linear potential, which is kind of the general form of the linear potential is v is negative kx. So you see it's a linear function of position, linear function of x. See, an electron, a simple example, an electron of charge negative q under the influence of a constant electric field E, so it will move in a straight line along the direction of the field, right? We all know this from basic electrostatics. And the force due to electric field is QE. Q is the charge and E is the electric field strength. So electron's potential energy will be what? Potential energy, what is the relation between force and potential energy? Potential energy and force, it's actually the force is the kind of the gradient of the potential energy, of course. Negative del u del x, force. This is negative del u del x is force. So the potential energy will be, you can understand it like this, the potential energy will be negative q e into x. So if the electron covers a distance x in the direction of the electric field E, and the charge of the electron is negative q, then the electron's potential energy will be negative q into E into x. So q is a constant electronic charge and E is the electric field strength, which is also constant. We are not talking about a time varying electric field, so it's a constant. So that means this expression negative QEx, you can write it as negative Kx, where K is a constant QE, and this is an example of a linear potential, a linear function of x. And in this case, in place of minus v, we can write minus Kx, that is plus Kx. So this will be our action. Quadratic potential is also very important in the microscopic world because harmonic potential energy is quadratic. We know from very basic knowledge of classical physics that harmonic oscillator, the potential is given by half Kx square. The force is F equals negative Kx, restoring force, Hooke's law, restoring force, elastic, and all these things we have learned. Even in high school we have learned. And the potential is, you can calculate it, it is half Kx squared. This is a quadratic potential. And why is this important even in quantum mechanics? Because we often, not only quantum mechanics, in solid state physics as well, because we often model the structure of crystals as atoms arranged periodically in the form of a lattice, with the atoms connected to one another by springs. Okay. So yeah, this is the nature of, this is why quadratic potentials are also very important. And it describes oscillator as simple harmonic motion. And it's quadratic because it's a function of x squared. So in this case, this will be the action. We have, in place of v, we have half kx squared. Now let me quickly show you how to deal with the mathematics. Now you will not understand all the steps. Let me be very clear. You will not understand all the steps if you have not watched the previous video probably. So like I already said, this is supposed to be a continuation of that video. So I will be assuming you know how to calculate. You have seen the derivation in the previous video I have discussed very elaborately. I will be assuming that you know how to calculate the free particle propagator, how to calculate the path integral for a free particle very elaborately. Now we'll be doing the same for a particle with a non-zero potential energy, no longer a free particle. So things will of course be a bit more complicated. So first we'll be starting with the action. Now here we have just assumed a general arbitrary potential energy Vx, not linear or quadratic. So the propagator is defined like this. Again, this is, I have already derived this expression in the previous video as well. This is the general form of the propagator. General form. We're not about any free particle or particle with potential. And this is my action. So in the expression of the propagator, you have e to the I s over h bar. So in place of s, you should put this value of action, right? Now we'll proceed by dividing the time interval. This is the similar approach we have followed for the free particle as well. So you should be, I'm assuming you are familiar with that. Now we will proceed by dividing the time interval Ta to Tb, the full time interval, into n equal parts with the intermediate time points being T1, T2 and so on and so forth. Like Ta is the initial time point which will be saying T0, and Tb is the final time point which will be saying Tn, because there are n time points. And yeah, it will be like T0, T1, T2, T3 and so on up to Tn minus 1 and then finally Tn. And the x values will be accordingly x0, x1, x2 and so on to up to xn minus 1 and then xn. So now we will discretize the action S, which is now not as straightforward as before because of the presence of the additional potential term. So we'll be focusing on a small line segment. Okay, so you can think of it like this: from A to B, there is a line. There are many possible paths. So let us focus on a small segment in the ith time interval. Let me show you this picture. This will make things a little more clear, I think. Okay, no, not this. Yeah, even this will do. See, this is t0, t1, t2, and so on till tn. So there are n time intervals. So let's say we are considering the ith time interval, this one, ti and ti plus 1, this line segment. When I say line segment, I am talking about this particular line segment for the ith time interval. And corresponding value of a, this will be xi and xi plus 1, corresponding x values. And this interval is, of course, all the time intervals are epsilon. Okay, so yeah, corresponding to the ith time interval, ti and from ti to ti plus 1 of a path among all the paths from A to B, I is like arbitrary, any intermediate time interval. So for that particular line segment, I already showed you the picture. Then the corresponding position interval will be xi to xi plus 1, and essentially we are concentrating on one small portion of the path between the points ti xi and ti plus 1 xi plus 1. So the slope of the line segment is clearly dx over dt, that is the difference in the x values, xi plus 1 minus xi over ti plus 1 minus ti, right? And this is epsilon, the time interval. So this will be xi plus 1 minus xi over epsilon. This will be the dx dt, the slope of the line segment. And the midpoint is, of course, the midpoint will be ti plus 1 plus ti over 2, comma xi plus 1 plus xi over 2, the midpoint of this line segment. So the particle's kinetic energy, it's easy to calculate. It's half mv square, which is half m. In place of velocity, we can write dx dt, and in place of dx dt, we can write this expression we got right over here, and then we can write half m xi plus 1 minus xi whole square over epsilon square. This is my kinetic energy T. Now, to find the expression for the particle's potential energy, here's a little bit of assumption. You can say it's a kind of assumption. I cannot explain this. But we will focus on the midpoint of this line segment, which we defined this way, right? The midpoint. So we will assume that the potential energy, since we say that the potential is only a function of position and not time, so V was Vx. Now in place of x, we will be writing the midpoint. So we will be writing the potential energy V as Vxi plus 1 plus xi over 2. So we just assume the potential energy to be a function of the space variable of the midpoint. This is a valid assumption because we take the midpoint. But of course this is an assumption. It's not it cannot be derived. This is an assumption. So now we can write the action for this particular line segment. See, I'm writing SI, not the full action. I'm writing the action only for this line segment. That's why the integration is from Ti to Ti plus 1. And this is the Lagrangian. And yeah, so this will be what? T minus V epsilon. Because dt is just epsilon. You are integrating over only one time interval of length epsilon. So instead of this integration, this time integral dt, we can just write T minus V into epsilon. So that means we can write, this is the kinetic energy expression multiplied by epsilon. So there was an epsilon squared here. So you will be you're left with this, and this is the expression for v into epsilon. So epsilon into v. In place of v, we have written say v as a function of the midpoint. So this is my action for the ith line segment. Si, the action S of the particle for only this portion of the path for ith line segment. So the total action, you will just add up the contribution from all such actions. So the general form will be like this, right? First you put I equals to 0. So then it will be x1 minus x0, right? x0 is basically xa. And then this will be like this. Then for I equals to 1 and so on. And finally you will do it for I equals to n. So for I equals to n, you will get xn plus 1 minus xb, because xn is the same as xb, the final point. So I have written xb minus xn minus 1, because ultimately you see it is squared, it's whole squared. So whether you write a minus b whole squared or you write b minus a whole squared doesn't really matter, right? And yeah, just a second, I will run from n plus 1, n minus 1. Oh, I think you can I think you will put I will n minus 1 actually. Sorry, this was wrong. For this last term, last term, you are actually putting I equals to n minus 1, because I is the number of. Let me show you why. Let me show you. I'm really sorry for the confusion. You see, this is the see, I will be what? This is I equals to 1. See, I equal to 0, I equal to 1, I equal to 2, and so on. This is I equal to n. But you will not consider this because the final point and the initial point, they are already fixed. you will consider up to this, you will not consider this point. So you will put I equals to n, you will go up to I equals to n minus 1, right? So that means you see I equals to n minus 1, I equal to 0 to n minus 1. Yeah, you can you are starting from 0 and you have n points, so 0 to 1, I mean 0 to n minus 1, that makes sense. Once more, sorry, but once more. See, you are starting from 0, I equal to 0. So I equal to 0 corresponds to this line segment. I equals to 1 corresponds to this. So I equals to n minus 1 corresponds to this line segment. So you cannot put I equal to n, that because you have nothing beyond, right? So since you are starting from 0, you will go up to I equals to n minus 1. And if you go up to I equals to n minus 1, you see the final term will be this. You put here, you put n minus 1 here. So x n minus 1 plus 1, that means xn or xb, and minus xn minus 1. xb minus xn minus 1, and so on. So this is your full action, the entire action, and the kernel is what? This expression, e to the I s over h bar. So now you can write it like this. You have n such parameters 1 over a, so you can just write 1 over a with each such expressions, and in place of s you can write what you got here. You got n terms, right? You start from 0 and up to n minus 1, so you get n terms. This is the first term, this is the second term, and dot dot dot, this is the nth term. So basically you have e to the I s over h bar, so s has n terms, like a plus b plus c, like in addition. So exponential in the power, if you have addition, you can write it as product, right? E to the a plus b is e to the a into e to the b, right? So you see, I have written it in product form. First e to the I h bar, the first term, then dot dot dot, these are all products, and finally this is the last term, e to the I h bar, last term. So there are n products and there are n 1 over a. So with each product I have put a 1 over a. So this is my expression for the kernel. Looks very complicated, I know. Right. Fine. So now we'll be discussing the path integral for linear and quadratic potential. This is for the general. Here we assume the general potential Vx. Now for see, first let's consider a potential that is linear, like V equals minus kx, this expression, this form of potential. So the action will be so on and so forth, blah blah blah, the same thing. Yeah, in place of V we'll be writing plus kx, in place of minus V we'll be writing plus kx, because V is minus kx now. And yeah, again this is the expression for the kernel. Yeah, now here we'll be following a different algebraic method, you can see. First we start with the path for which the action is minimum, and we denote it by x bar. So this is the classical path. Of course, this is the path of least path, or the path of least action. Now any arbitrary path x between a and b can be expressed as the classical path plus some disturbance or some variation. So this is the classical path. We have defined x bar, and x bar plus eta, where eta is any arbitrary variation. We can, using appropriate values of eta, you can define the other paths as well. You're basically defining the other paths as a variation about the least path x bar. So x is x bar plus eta. Now note that the initial and final points are fixed. So at t equals ta and t equals tb, we must have x equals x bar. Because at t equals ta, that means the initial point, there is no variation. Eta is 0. Because it's a fixed point. And similarly at t equals to tb also there is no variation. I mean, I'm talking about this. This is the fixed point. This is a. So at t equals to ta, there is no variation. You have only one point. So eta has to be 0. X will be equal to x bar. And same at b. But suppose this is the least path x bar. So for intermediate points, maybe you want to describe this path x. Then there will be some variations. Some variation here. Some variation here. There will be some variations in the intermediate points, because there are many possible paths. But since the final and initial points are fixed, there will be no variation. So I mean, at t equals to ta and t equals to tb, we must have eta equals to 0, because x has to be equal to x bar. Now let's expand the expression for the action action s about the least path x bar. So this was my action s, and so in place of x, I'm just writing x bar plus eta using the above expression. So dx dt will be dx bar plus eta dt, and yeah, kx will be kx bar plus eta, like this. And we just break this up, right? We just this was whole squared, so we just break this up, dx bar dt plus d eta dt, and whole squared. And we further simplify. Look at the simplification. We have m over 2, we have dx. So this is basically a plus b whole squared. You see, a plus b whole squared. That's what I've done. A squared plus 2ab plus b squared, right? Now you take all the x bar terms together. So here we have an x bar, here also we have an x. Okay, keep this out for now, and here we have an x bar, kx bar. So you group this together, these two terms you group together. Okay, and what else do you have? This term you just write it here. Okay, so this term we have a m over 2 outside, so this 2 and this 2 will cancel, so we ultimately have m dx bar dt d eta dt, and finally we have k eta from here. From this we have k eta, and we have this term here, m over 2 multiplied by d eta dt whole squared. Now this expression right over here, I'm talking about just this term in terms of x bar. So you just write it separately, and write this separately, and write this separately, nothing much. Now the first integral, I mean this expression right over here, this is essentially the original action s evaluated at the least path x equals to x bar, because original action was what? This was my original action. Inside the time integral we had m over 2 dx dt whole square plus kx. Here also we have m over 2 dx bar dt whole square plus kx bar. So this is just nothing but the original action, except you put x equals to x bar in the original action. So in this we can write s naught. This is my original action s, and for x equals to x bar, since it's the path corresponding to the least action, least path, so we can write this as s naught, the least action you can call it. So this is s naught. Okay, fine. Now let's look at this integral. Let's evaluate it by parts. So integration by parts, we all know that we have a formula for integration by parts, right? Integral u v dx, where u and v are both function of x. That will be u integral v dx minus integral du dx integral v dx as a whole, right? And whether u will be the first function or the second function, you have this Eilert rule and so on and so forth. These are very basic elementary level mathematics. But anyway, using this formula, using integration by parts, what we can do is, you see, we can evaluate this integral. We have time integral ta, tb and this thing. So here we assume this to be the first function, dx bar dt, and eta to be the second function. So integration d eta dt will give you simply eta, because you have a time derivative and you have a time integral. So here this is eta, and the limits are ta to tb, negative of this thing. So here you will be taking the derivative of dx bar dt, so that will become a double derivative, and then you have again have eta dt and integral. Now I already told you that at t equals to ta and t equals to tb, eta is 0, right? So yeah, that means the first term vanishes, because this is evaluated. We have an eta here, so we will put tb once and we will put ta once. The limits are tb and ta, so both will be 0. Eta will be 0 in both the cases, and eta multiplied by anything will also be 0. That means the first term vanishes, and ultimately in place of this integration we can write negative, just this second term, negative integration d2 x bar dt squared eta dt. Thus in the original expression, here we can write s naught, here we can write this new expression, and this will be as it is. That's what we have done here. A is equals to s naught minus this plus this. Okay, and this also we have just broken it up, and we have written it like this. Yeah, look at it. Here we have k eta plus m over 2 d eta dt whole square dt. So we have just broken it up, and we are regrouping these two terms. Both of them have this eta dt. So we have taken eta dt, we have kept eta dt outside the brackets, and inside the bracket we have m d2 x bar dt square minus k, and this is the remaining part. Okay, so now we can write now since s naught is the action for the least path or the minimum action, so s equals to s naught for up to first order variations in eta. In other words, we can say that the action does not change much around the minima for up to first order variations eta. Of course, I mean, if for a minima or a maxima, the first order derivation will be 0, a derivative will be 0. The second order derivative will be either positive or negative depending on whether it's a like minima or maxima, but yeah, the first order derivative will be 0. So that by this logic we will be ignoring this third term, because here we have d eta dt which will be 0, the first order derivative. So if this is 0, then this entire term goes to 0. So we ignore the third term and we are left with the action s. I'm sorry, this is a typo, this will be s. So no, this is not a typo, wait. So we are ignoring the third term, fine, but we can ignore the third term only when s is equal to s naught. I mean only since S naught is the minima. S is the general expression for the action. S is not S naught. But when S is equal to S naught, that means for the special case when S is the minima, then we can ignore the third term. So that's why in place of S we have in the LHS in the right hand side of the in the left hand side of the equation we have S. So since we are doing this for S equals to S naught, we have written S naught here, and now we can write this expression. Like now we can ignore the third term and write just this. So we get logically we can say that S naught equal to S naught minus something. That means this something has to be 0, because S naught will be equal to S naught. So this something has to be 0. So the time integral of this thing has to be 0, and eta is arbitrary. You cannot put eta to be 0. So that means this quantity inside the bracket must be 0. That means yeah, this should be 0. Now if we use this result back in the original expression, of course we derive the result under a special condition, under a special assumption that S equals to S naught. But if even for this single particular special case, if this expression is 0, that means this has to be 0 everywhere else. This value cannot change, right? So now by this logic, in the original expression for the action, we can use this result, and we can put this to be equal to 0. So if we do that, we get S equals to S naught plus this. You see, S equals to S naught plus this, because this term goes to 0. I hope the mathematics is clear to you. Now denoting this integral by S eta, we just suppose denoting this by S eta, we can now write that action S is equal to S naught plus S eta. So see, we started by defining the any arbitrary path as a variation over the least path, a variation about the least path. So x bar is the least path, eta is the variation, arbitrary variation. So we defined x to be x bar plus eta. Similarly, after some mathematical algebraic manipulations, we can define the action S to be S naught, the least action, plus some variation S eta. Now using x equals using x equals x bar plus eta, we can write xi equals xi bar plus eta I for all I line segments. We already know that we have divided the entire path into I line segments, right? Then in that case, dxi will be dxi bar plus d eta I. Now dxi bar will be 0 again. This of course, because xi bar will be the least path. X bar was the least path, right? So xi bar will also be the least path for that particular line segment, for that particular portion of the entire path. And since it's a minima, its first order derivative dxi bar will be 0 for all I. That means dxi we can write d eta I. See, dxi will be d eta I. The dxi bar will be 0. So from this logic, dxi will be d eta I. Now let's go back to the expression for the kernel, and we can rewrite the expression like this, just a simple mathematical manipulation. Okay, what I've done here is essentially in place of dx, I have just put d eta. For all the values of I, we can write dxi to be d eta I. That means dx n minus 1, I can write d eta n minus 1, dx n minus 2, I can write d eta n minus 2, and so on. That's what I've done here, nothing more. You can think of it as a change of variables from x to eta. Now we also know that s is s naught plus s eta. So e to the I s over h bar, this expression that we have right over here, we can write e to the I s naught plus s eta over h bar, because s is s naught plus s eta. That is e to the I s naught over h bar into e to the I s eta over h bar. Now this is constant, e to the I s naught over h bar is constant, s naught is fixed. So you can take it out, we can take it out of the integration, and we can write the final kernel from a to b as e to the I s naught over h bar, and then we can write the rest of the expression. So this is just like the original expression for path integral, but in terms of eta now. Here also we have e to the I s eta over h bar. And now we will, here it's a kind of assumption. Okay, there are a lot of assumptions for this method to work. See, actually calculating path integrals for a particle with a non-zero potential is very, very complicated. So whatever I'm showing you, this method, you can say it's kind of an approximate. Like we started with x equals x bar plus eta and so on and so forth. There are a lot of assumptions. But under these assumptions, in this method, we will treat this remaining, this entire expression as a constant. Let's say c. So yeah, it's not possible to evaluate this integration directly using this method, but it will be a constant. So now we can write this entire kernel as some constant c times e to the I s naught over h bar. That's what we have written here. So right now we are considering, we did all of this for the linear potential v equals negative of kx, right? So now we will need to find an x bar that minimizes the action s, where the minimum action is denoted by s naught, right? So Just a second. Yeah, this is the expression for s naught, because the expression for the action was this thing. Let me show you. The expression for the action was this thing. Inside the time integral, we had m over 2 dx dt whole square plus kx. So if we put x equals to x bar, that will be the least path or the least action. So then s will be equal to s naught, and that's what we have done. M over 2 dx bar dt square plus kx bar. Just put x equals to x bar. And again, we'll be introducing a small variation eta about x bar, so that x is x bar plus eta, and we'll be following the same mathematical procedure that we did just now. But now we will be doing it with slightly different goal in mind. Okay. Here also we can write the action s bar as s naught plus this and so on and so forth. But here what we'll be doing is, let me show you. Yeah, again we arrive with the same result. M d2 x bar dt square minus k equal to 0. Yeah, we actually already arrived at this result here. You see, m d2 x bar dt square minus k equal to 0. So the same result I have written. I have once more written it here. M d2 x bar dt square minus k equal to 0, which means m d2 x bar dt square equals to k. Now look at the expression m d2 x bar dt square. Now d2 x bar dt square is an acceleration term, right? And m is mass. So that is basically mass into acceleration. This term m d2 x bar dt square is reminds you of Newton's law, F equals ma. Now here x is not any, like, not the position or not any arbitrary position. X is the least path, x bar. Okay. So yeah, this is actually a second order differential equation. D2 x bar dt square equals to k bar. You can write k prime, where k prime is just k over m. You just divide by m both sides. K prime is k over m, which is a constant. Now you integrate this. Now essentially we will try to solve this second order differential equation. So first you integrate this to turn it into a first order differential equation. So you are left with dx bar dt will be equal to k prime t plus the integration constant c1. Now we will integrate this again with respect to time. Then we will be left with just x bar will be k prime t square over 2 plus c1t plus a second integration constant c2. Now this is the equation of a parabola. You see, on a x versus t, suppose you are plotting x versus t. So then you see this is x is a function of t squared. It's a parabola, and these are all like, okay, this is not really a parabola because we also have a linear term, but yeah, it will resemble a parabola, right? So that means the least path x bar is a parabola in this case. Now here is I think I'll skip this part actually. Here we have just kind of evaluated the constants c1 and c2, or let me just discuss this for you, no problem. So at the point t equals to ta, x bar will be xa, because see, this is the initial point. At the initial point, whether it's the least path, whatever path, x is always xa, and similarly for t equals to tb, x bar will be xb. So putting t equals to ta and x bar equals to xa in the above equation, I mean in this equation, we can say that xa equals to k prime ta squared over 2 plus c1 ta plus c2. So from here we get an expression for c2. Now we put t equals to tb and x bar equals to xb in this equation once more, and we get xb equals to k prime tb squared by 2 plus c1 tb plus c2, and again we get an expression for c2, right? Sorry, yeah, here we get this, and now we already have an expression for c2. Now we will put this expression in this equation in place of c2. So we do that, and on doing that we get this. So see, in this equation we have only c1. We have kind of eliminated c2. So now we need to evaluate c1. Now we find an expression for c1. Okay, we can do it from here only. So c1 will be what? xb. We have an xb here. See, we have an xb here. xb minus k prime over 2 tb squared minus t squared. We just take this term to the other side. So that's what we have done. xb, then minus this term, and here minus xa as well, minus xa, because we have a plus xa here, and then we are left with c1 tb minus ta. So we divide this entire thing by tb minus ta, right? That should give me c1, and that's what I've written here. So now we have an expression for c1 as well. So now the complete expression for x bar will be, so now we have an expression for c2 as well as a c1. So in this equation x bar, we now in place of c1 and c2 we will just substitute these expressions, and we get this complete expression for x bar, which is very complicated, but yeah, this is what we get. So now let's evaluate dx bar by dt whole square. So let's just take the derivative of this expression. So we take the derivative, and we take the whole square of the derivative. We square our result, right, basically. So we just do that, and we get this. We start with the simple expression with that contains C1 and C2. Here we don't put the values. Here we don't use this expression. It's very complicated, right? So now we can write S naught, or the least action, as follows. Least action was this, right? Now we have an expression for x bar. See, we already have an expression for x bar. To find this expression, we did so much to find the value of C1 and C2. So we can put in place of x bar, we can put this expression, and now we also have an expression for dx bar dt whole squared. I mean, yeah, this expression right over here. So we just put all these expressions. Here we have just kept the constants C1 and C2 just to keep things simple. So after some simplification, we get an expression like this in terms of C1 and C2. And of course, we assumed k prime to be k over m. So k will be m into k prime. And using this and again simplifying, we get this thing. So I'm skipping a bit here. You can just check it out by pausing the video. Or if you want to take a screenshot, you can go ahead. Fine. So yes, now I think, yeah, now we have found a general expression for the action S naught. So now we can use the above expression for S naught for a particle with a linear potential energy and write the path integral from A to B. Now we can write the path integral KB, A. We in this method, under our assumptions, we wrote the kernel as some constant C into e to the I S naught over H bar. And now we also have an expression for S naught. So we just put this expression here in place of S naught. And this is the expression for my kernel for a linear potential energy. It's very complicated, I know. Now in this expression, if we put k equal to 0, which means k prime will be equal to 0, because k prime and k are just related by a factor of constant mass m. So if we put k equal to 0 in the expression for the least action, if we put k equal to 0 in this expression, S naught in this expression, putting k equal to 0 means putting k prime equal to 0, then we get this expression right over here. And if we put k equal to 0, or in other words k prime equal to 0 in the expression for C1, we get this. You can all check it out. You can just check it out manually on pen and paper. So under the assumption that k prime equal to 0, the least action can be written like this, which is the free particle action. If you try to if you watch the previous video and if you try to tally it with your knowledge of free particle propagator, free particle action, because in free particle action there is no potential energy, right? And the potential energy was, in our case, we assumed it to be minus kx, linear potential. But putting k equal to 0 or k prime equal to 0 means there is no potential. That means essentially we're talking about a free particle. So that means the expression we derived is right, because under the assumption that the k is 0 or the potential energy is 0, we get back the expected expression for the free particle action, which is a good thing. Now let's find the least action for a quadratic potential energy. Okay. So now in place of V, we'll write a half kx square, of course, and now we will be following the same procedure. So I'll be going through this a bit more quickly. But I'll give you enough time to take screenshots in case you're interested in, trying to do this by hand and later verifying with with this document. Take a screenshot now if you're interested. Fine. You can take a screenshot now. Let me just quickly do away with the screenshots because I might forget as I proceed. And you can take a screenshot now as well of this portion. And finally, I think this is, you can take a screenshot now as well. You can take a screenshot here. You can take a screenshot. I think this should be enough. Okay, second last, I guess. And okay, some more. And let's proceed. Yes. And you can take a screenshot. Okay, so let's quickly go through this quadratic potential also as well. So now when we talk about the quadratic potential, we'll be following the same procedure. So I'll be, like I said, not be discussing in very detail, but we start with this least path x bar, and we find an action S naught, the least action. We assume x equals x bar plus eta. The same thing, then we do these manipulations and then we integrate by parts, the group, ungroup and group terms and all. Only difference being here we have minus half kx squared and not just minus kx. Nothing, no more difference. So following the same procedure, you should get s prime equals to s naught plus this expression right over here. And by similar logic, you will actually see that in this case, this thing should be 0. No, not this, I'm sorry. You should get like this thing should be 0. Just a second, I myself got confused. If you integrate this by parts, you should get this, and again the first term will be 0 and you will be left with this term. So fine, so far so good. And you will do this. Okay, finally you come here, and now you can put s prime equals to s naught, and now you can say that okay, so this term has to be 0, this term. So m d2 x bar dt square plus k x bar should be 0, which means m d2 x bar dt square is negative k x bar. And the above equation looks familiar because this is nothing but Newton's law of motion for simple harmonic oscillations. Hooke's law. What was Hooke's law? Force F equals minus kx, right? X is restoring force, x is the displacement. So here in place of force you can write mass into acceleration, m d2x dt square. So m d2x dt square is minus kx. So this is the same equation, but in place of x you have x bar, which is the classical path, least path. So basically this shows why the path integral is only a more general case, but the classical physics is only a special case of quantum physics. So when you have the classical path, for the classical path even the laws of quantum mechanics will lead you to Newton's law, for the familiar laws of classical physics. It's a very beautiful kind of observation, right? So if you assume the least path x bar to be the displacement of the mass m with spring constant k undergoing simple harmonic oscillation, then m d2 x bar dt square is the force mass times acceleration, which for simple harmonic oscillations is negative k x bar, as we know. As the solution of the above differential equation, we already know it's pretty simple to calculate, to evaluate. It is this kind of solution. X bar will be a cos omega t plus b sin omega t, where omega is under root k over m, right? That's how we define. K, we have a k here, right, and we have an m here, so omega is under root k over m, and a and b are constants. Now again we can determine the constants like we did, because again at t equals to ta, x bar will be xa, and for t equals to tb, x bar will be xb. And let's assume ta comma xa to be 0 comma 0, the initial point to be the origin, the mean position you can say. So that means x bar will be 0 when t equal to 0, and x bar will be xb when t equals to tb. So that means we can put both x bar and t to be 0 in the above expression, and then we'll get 0 equals to a cos 0 plus b sin 0, which means just a, because sin 0 is 0 and cos 0 is 1. So that means a equals to 0. From here we can say a equals to 0, and that means our expression collapses to x bar equals to b sin omega t. Now again if we put if we put x bar equals to xb, so and t equals to tb, so we can write that xb equals to b sin omega tb, which means the constant b is actually xb over sin omega tb, and our final solution is x bar is b sin omega t, right? So that means in place of b we can write xb over sin omega tb and then sin omega t. So this is our final solution, x bar. Now we can also find out dx bar dt and its dx bar dt whole square, basically just a simple time derivative. We can do that, and we had, this is the expression for s naught, right? So in place of dx bar dt whole square we can put what we got above, and in place of x bar also. So doing that, and after some simplification we arrive at here, and some algebraic manipulations which I'll be skipping because it's very simple to follow actually, although it's a bit lengthy and it might look mathematically heavy, but it's pretty simple to follow. So we arrive here. Now we assumed ta to be 0, and so if we put ta to be 0 and k is omega square m, since omega was under root k over m, we get the least action s naught as m omega xb squared over 4 sin square omega tb sin 2 omega tb. And using sin 2x equals 2 sin x cos x, we can again further simplify it and write it like this. And yeah, this the assumption we assumed like that tax at the initial point is the origin. This reflects that the body starts to oscillate from the mean position at the origin. I mean, we can define the origin anywhere, right? That's in our hands. We have a freedom of choice there. Now in the limit omega tends to 0, we can say that cos omega tb tends to 1, because for cos 0 is 1, and sin omega tb tends to omega tb, because for very small values of theta, sin theta tends to theta. So in that case the above expression reduces to m omega xb squared over 2 omega tb, or you can just cancel out the omegas and you are left with what? M xb squared by 2 tb. Now xb over tb is a velocity term if you think about it, distance over, so that means you can write m xb squared over tb squared, that means half mv squared into tb, because see this is very important. Let's just multiply divide by tb. So you have an extra tb here, you have multiplied by tb, and since you have also divided by tb, we have tb squared here. Now xb squared by tb squared is kind of v squared, velocity squared. So that means you can write half mv squared, which is the kinetic energy, into tb, into time. So you can, we know that the action is kind of the time integral. That means it, the dimension wise it's energy into time. So you see it's energy into time. It all fits in. And this is the action for a free particle, right? S naught is the least action. That means of course that's why there is only kinetic energy, no potential energy. So this is the action for a free particle. Because we have assumed omega tends to 0, and omega is under root k over m. So omega tends to 0 means k tends to 0. And k tends to 0 means our potential half k x square quadratic potential tends to 0. That means no potential energy. That means free particle. And for a free particle, the action is just kinetic energy, that's half mv squared into time. That's what we're actually getting. So this all makes sense. Now we calculate the propagator for a particle with a quadratic potential energy in the same method. Again we can do the same thing, and ultimately we'll get the, under our assumptions we'll get the same thing, like k will be some constant times e to the I s naught over h bar. Yeah. So I think I covered this topic in sufficient detail. The topic of both linear and quadratic potentials, free particle, propagators for particles with non-zero potential. Free particles I've already done in that video. Yeah, now in that video I have already discussed this thing. Okay, let me just quickly show you this. This thing, Schrodinger's equation for a free particle. Since I have discussed free particle propagator in that video, that knowledge was sufficient to derive this. That knowledge is sufficient. So we started with the multiplicatives of propagators, and then we introduced a wave function, and then we just did some algebraic manipulations, and essentially we started with the free particle propagator, since we are doing the Schrodinger equation for a free particle, and then we arrived at this result. Schrodinger's equation is, let me show you. Schrodinger's equation is this equation, right? So for a free particle, potential is 0, so this term will not be there. So for a free particle, Schrodinger's equation is this, which we derived in the previous video. Now in today's video, for the remaining part of today's video, we'll be showing how we can also derive Schrodinger's equation for a particle with a non-zero potential. I mean this entire equation. Since now we know how to calculate the path integral for particles with potential, now we have a basic idea. So now we'll be talking about Schrodinger equation for a particle in the potential field. Now again here we'll be using this assumption that potential as a function of position, like v equals to v, we'll be considering the midpoint of that line segment like we did, right? V equals to xi plus 1 plus xi over 2. So we start with the kernel. First we start with the kernel of only that midpoint. Only that line segment from I to I plus 1. So that the kernel for only that line segment will be what? Ti plus 1 comma xi plus 1, the final point, to ti comma xi. So that kernel we can write it like this, right? 1 over a e to the I s over h bar. In place of s we can write this. We already derived, we already discussed this when we were starting our discussion on action for a potential. I mean action for a particle with a potential. Yeah, here also we discussed this, right? Action with a non-zero potential energy term, we discussed this thing. See, this was what we are getting. The kernel. See, this is the expression. The kernel for that line segment, and the total kernel we can the total action we can write it as sum. The total kernel also we can like sum it up. So this same expression that we already discussed, this is what I've written here. Nothing more, nothing new. Okay, give me a second. Yes. Oh, I'm sorry. So this is what I've written here. You see, this is the action, the kernel for that line segment I to I plus 1. And now we can rewrite the propagator using ti equals to t and xi equals to y. This is just some notation. Again, I'll not be going into the details, but this notation I'm using because we used the same notation when we were discussing the Schrodinger equation for a free particle in the previous video. Nothing more. But using some change in variables, we can rewrite this equation in this form. And see, now we're working with the kernel with a potential term, because of course we are trying to derive the Schrodinger equation for a non-zero potential energy particle. And again, this is actually we are rewriting the multiplicatives of propagators, but in a different way. So this kernel right over here, this kernel we are replacing with wave function, and this kernel also replacing with wave function, but this intermediate one we are keeping it a kernel, because here both the roughly speaking the wave function is only interested in a fixed point. Like what is the probability that this is the state of the particle, but the kernel is more interested in the time evolution of the particle, like from initial point A to initial point B. Anyway, I have also explained this very clearly in the previous video, so I'll not go deep into this here as well. Just a second. Yeah, so this is now this we already had, and now in place of kernel, in place of k, now we will use this expression, because now we are no longer talking about a free particle, we're talking about a particle in a potential field. So we do that, and then we introduce a new variable eta equals y minus x, just a change in variable, d eta equals dy, because x is a fixed final endpoint constant. So see, I understand that I kind of rushed through this part, but and it's not really possible for you to understand this, like why x is the fixed final point, because to understand the convention or the notations we have used here, you should watch the previous video, I think. I mean, anyway, you should anyway watch the previous video, but whatever. But doing all that, we get this expression right over here, and again we'll be using Taylor expansion, the same thing we used in the previous video as well, when we were deriving the free particle Schrodinger equation. So using Taylor expansion of all these terms, psi t plus epsilon x, psi t x plus eta, using the Taylor expansions, and we will only be considering up to first order terms, and then we get this, and we will also Taylor expand this potential v x plus eta over 2, and then we get this, and using all these results in the initial expression for psi, we get this. Again, it's very difficult to follow, I understand, but it's not possible for me to see. It's not really required. If you are comfortable with the notations, which it's not possible for me to cover from the beginning in this video, then I think you'll be able to follow the steps. It's useless to kind of read out these steps out loud. But yeah, ultimately we're getting this. Now all terms that do not depend on eta, like this. Now see, we're kind of separating all terms that do not depend on eta, and we'll be treating them as constants, because the integration is with respect to eta. We have d eta. So doing that, we will see. We will just do a kind of comparison with between the left hand side and the right hand side, and we will get this result. And we have already previously obtained this, and using all of this, we can we'll get an expression for 1 over a as well. And using all of this, yeah, ultimately, I think I'll be skipping this part. Ultimately, you can show that you arrive at Schrodinger's equation from this. Okay. So yeah, now one point I would like to discuss two more important things before I finish off with this video. Just two more important things. Okay, one is there is a conceptual difference between the wave function in the canonical formulation of quantum mechanics and the path integral and the propagator in the path integral formulation. I already told you very briefly that path integral contains information about the time evolution of the particle. It's more interested in asking what is the probability that the particle goes from initial point A to the final point B. But the wave function is not interested in the initial point. It only asks what is the probability that the particle will be at this point. The final point will be B. What is the probability of that? Initial point is not that much important in the canonical formulation, in the wave function. So we'll be let's explore the conceptual difference between the wave function and the propagator using some plots. I mean visually. So yeah, in the canonical formulation of quantum mechanics, the wave function of a system denoted by psi essentially contains all the information that can be known about that system. We already discussed all of this, right? And this probability, density, probability, and all of this. Okay. So now a basic constraint on any physical system is that it must exist somewhere in space. I mean, if it doesn't exist anywhere in space, then it's not a physical system at all. So in other words, if we consider all the space in the universe, that means if the limits of the space integration over the position variable is minus infinity to plus infinity, then the probability of finding the system or particle within the entire universe must be 1. I mean, the particle must be somewhere in all of space, right? And that is the normalization constant. Integration from negative infinity to positive infinity of this probability, that's mod psi squared dx, must be 1. And a wave function describing a real physical system must satisfy the above condition. Otherwise, we cannot say it's a physical system, it's a real system. So we see that the wave function must be normalized. And this ensures that if we calculate the probability of finding the system in some finite region of space, we always get a value between 0 and 1. Now, if we consider all of space, then of course we get a probability of exactly 1. But even if we don't consider all of space, the value must lie between 0 and 1. It cannot go above 1 and it cannot come below 0. Since the wave function is theorized to be essentially a wave, we start by assuming psi to be described by the classical expression for a wave, that's a e to the I kx minus omega t. So here we have, for simplicity, we have assumed a one-dimensional system. So We don't write k like just k dot r. If we write in three-dimensional plane waves, we use k dot r, where r is a 3D vector, like x I cap plus y j cap plus z k cap. But yeah, here for simplicity we are just considering one dimension only along the x direction, and so a e to the I k x minus omega t. That's my wave function psi. I mean, we start with this expression. This a is the normalization constant. We have to choose a value of a that ensures that the psi satisfies this condition. Okay. Now, you see, it's interesting and important to note that Schrodinger did not derive his equation. In fact, Schrodinger equation is a fundamental postulate of quantum mechanics. Now, even though we can arrive at the equation for some specific cases, the equation cannot be rigorously derived for from some more fundamental principle. The role played by Schrodinger equation in canonical quantum mechanics is similar to the role played by the equation F equals to ma in classical mechanics. It dictates how the system evolves over time, whereas F equals ma tells how the position x of a classical system of mass m changes with time. Schrodinger's equation tells how the wave function of a quantum mechanical system evolves with time. Now, see, basically what I'm trying to say is that if you know psi, it is not enough to know everything, to know all the information about how the particle or how the quantum system evolves with time. So psi by itself, the wave function by itself, does not contain the information about the time evolution. For instance, if you know the position of a particle x in classical mechanics, in Newtonian physics, then can you predict, just with this knowledge, can you predict the time evolution of the particle, how the particle will evolve with time? No. For that you have to solve Newton's equation. You have to solve the differential equation F equals to ma. You have to solve the equation that F equals to m dx squared dt squared, which is a second order differential equation. You know the value of x, but only that knowledge is not sufficient to know the time evolution of the particle. You have to solve this equation. Similarly, only knowing the value of psi is not sufficient. You have to solve Schrodinger's equation, which is also a differential equation. You see, minus h bar squared 2m del square psi del x square plus v psi equals to I h bar del psi del t. So this is also a differential equation in psi. Of course, much more complicated than Newton's equation, but again, this is also a differential equation. So you have to solve this equation to get the information about the time evolution of the quantum system. The wave function by itself does not contain this information. That's what I'm trying to say. Here are some comments about relativistic quantum mechanics. I'll just keep it here, it's not required. Now see, now we'll look at the basic difference between the wave function, which is of central importance in canonical quantum mechanics, and the propagator in the path integral formulation. So we will confine our discussion to the free particle, which is a bad decision, but yeah, just for the sake of simplicity. Why do I say it's a bad decision? You will understand just now. So see, recall that the expression of the free particle propagator in path integral formulation, we already know this was the expression of the free particle propagator. And for simplicity, we assumed TB minus TA was just T and XB minus XA was just X, right? So we just assumed this. So let's just write it. And we also let's now calculate the real part of this this expression multiplied by under root I. We already did this when I showed you the plots with respect to position and time of this thing. So basically, real part of this thing, right? We have already multiplied with negative root I, so there will be no I in the denominator. So this thing, and the real part of this thing will be just, this is anyway a real quantity, and here e to the I x is cos x plus I sin x. So cos x is the real part and sin x is the imaginary part. So here the real part is just cos of this thing. What is this? Mx squared over 2h bar t. So this is my real part of under root I into the free particle propagator. Now let's look at psi. Psi is a e to the I kx minus omega t. Now in place of now using h over p equals to lambda, we know that h over p is lambda from de Broglie's relation, and we also know that lambda is 2 pi over k. So we can write that h over p equals 2 pi over k, which means h over 2 pi equals p over k, which means h bar equals p over k. H over 2 pi is called h bar, the reduced Planck constant, which means p equals h bar k. Similarly, we also know that E equals h over nu, and we know that nu 2 pi into nu is the frequency, so 2 pi nu is the omega, the angular frequency. So if we just multiply divide by 2 pi, we have h over 2 pi into 2 pi nu. That means we can write h bar into omega. So E equals h bar omega. So using p equals h bar k and equals h bar omega, we can write that psi, which was a e to the I kx minus omega t. Now in place of yeah, so we can just multiply divide this expression by h bar. Not the expression, we can multiply divide this thing, just the what do you call it, just the power of the exponential by h bar. So we divided by h bar, we have I over h bar, and we multiplied by h bar. So k into h bar becomes p. So we have px. and omega into h bar becomes e, so we have et. So we can write a e to the I over h bar px minus et. So this is a way we can write the wave function, right? Now for a free particle, we are just confining ourselves to free particle right now. So for a free particle, momentum p equals mv, which is mx over t, because v is the velocity position x over time t, and e equals half mv squared, kinetic energy, which is half m x over t whole square, which is mx squared over 2t squared. No potential energy since free particle. Now let's find out the real part of the wave function. Of course, whenever we are trying to understand how some parameter that describes a physical system varies with the position or time, we will be considering the real part. Like to keep the mathematics simple, in many cases we have seen that we use imaginary numbers, complex quantity, even in electronics, in LCR circuits, we use this imaginary number. But ultimately, the real, if you're talking about a real physical system, we will be working with the real part, right? So the real part of psi will be the real part of a e to the I over h bar px minus et, which is just the cosine, right? E to the ix, the real part of that is just cos x. So this will be a cos 1 over h bar px minus et, which is a prime cos 1 over h bar. So in place of p, I have written mx over t, and we have px, so that will be mx square over t, minus, in place of e, we have mx square over 2t square, so we will have mx square over 2t, because we have et and 1t will cancel. Okay, and yeah, in place of a, we have written a prime, just to take into account normalization constant and all and everything. Anyway, this a prime is just a constant. A prime is the expression is the real part of a, because in general even a can be complex. So if you're considering the real part of this entire thing, so we should write a prime. Actually, I should have written a prime here also. This is a, but once we have evaluated the real part, we should write a prime. Anyway, doesn't really matter very much. So the real part of psi is this thing. I'm just writing a here. Don't get confused between a and a prime. Just a constant. So this is a cos this thing right over here. Now if you just simplify this, this will be what? Just this expression. If you simplify, you can take mx square over t common, and you will be left with 1 minus half. So that's half mx square t. So that's basically mx square over 2t and 1 over h bar. So the real part of psi is a cos this thing. Now notice one thing. This is this is the phase of the real part of psi, mx square over 2h bar t. And what was the phase of the real part of this thing, the propagator for a free particle? That was also mx square over 2h bar t. So the phase is the same in both the cases. However, the amplitude of this normalizing factor, this is different. For the propagator, we see that the normalizing factor is a function of time. It's under root m over 2 pi h bar t. So it's a function of time. But in this case, it is just a normalizing constant a, and we know that this a cannot be a function of time. I mean, when we're defining the wave function a, this is just a normalization constant. This cannot be a function of time. So here we see a difference. The real part of the wave function, the amplitude is not a function of time, but there the amplitude is a function of time. And however, the phase is the same in both the cases. Because technically, yeah, both the wave function in canonical quantum mechanics and the propagator in the path integral formulation of quantum mechanics, both of them are kind of probability amplitudes. Okay, so yeah, that's what is written here. Phase is the same in both the expressions. Now to visually compare the free particle propagator and the free particle wave function, we will be plotting both the real parts of the wave function of the propagator as functions of both position and time. However, see, here's the catch. That's why I said it's a bad decision to choose the free particle, even though we did it for simplicity. We must keep in mind that we are only interested in studying the behavior of the real parts of propagator and wave function and make some general comments about the same. A physical interpretation may not be possible. Why? Because, see, a free particle wave function cannot be normalized. You can think of it like this. A free particle. So that means the particle is not under the constraint of any potential field or anything. So the particle, you can find the particle anywhere in the universe. It's free to move. Right? It has no potential energy, no potential constraint. It is not experiencing any potential. That's what I'm telling. So this is just an argument to make you understand why the free particle wave function cannot be normalized. But we can also think about it mathematically. I mean, we should actually think about it mathematically. So that means, what does this mean? The free particle wave function cannot be normalized. This means that a finite value of normalization constant a does not exist for the case of free particle. But to actually plot this in Python or whatever, you have to like arbitrarily set a finite value of a. If the value of a is infinite or undefined, the Python cannot generate a plot. So I just want to ensure that you understand what I'm talking about. To visually compare the wave function with the propagator, we are doing the plots and making some comments. However, technically, a physical interpretation may not be possible because to do the plots, we are assuming a constant value of a finite constant arbitrary value of a. But for a free particle in general, the normalization constant may not have a finite value. That's what I'm trying to say. See, let's try to normalize. Normalize means minus infinity to plus infinity integration mod chi square dx should be 1. So what is this? Let's try to evaluate. Mod chi square, since chi is a complex quantity in general, this will be chi star chi, where chi star is the complex conjugate of chi. So let's put in the expression for the free particle wave function. So when we have chi star, since it's a complex conjugate, we will have I don't know, we will have I in place of I, we will have negative I. So yeah, this will be a e to the negative I kx minus omega t and a e to the I kx minus omega t. So both these exponentials will cancel, right? And we are left with negative infinity to positive infinity integration dx mod a square, right? Now a is a constant, so mod a square will come outside the integration and you are left with integration dx, which is just x, but the limit of x is minus infinity to plus infinity. So that means what is this? What is the value of this? Infinity into mod a square minus infinity into mod a square. That is clearly undefined. So that's why for a free particle, you cannot say that this quantity is equal to 1, which is demanded by the normalization constant. So the above integral diverges, meaning it's not possible to normalize the free particle wave function. However, for our purposes here, it's sufficient to note that the normalization constant a that appears in the wave function is always independent of time. I already told you. And for generating the plots, we will arbitrarily choose a finite constant value of a, ignoring the fact that the free particle wave function cannot be normalized. Now see, this is the plot of the real part of the free particle propagator as a function of position, and this is the plot of the real part of the wave function psi as a function of position. Now you can see that this starts from, this is minus 10 to 10 and this is minus 0.4 to 0.4. So all of this we can ignore because this is the amplitude, right? So that depends on what value we have chosen for a. See, here we have chosen a 0.5, arbitrary value of normalization constant. But other than that, if you look at it visually, the nature of the plot is the same. Both the plots look exactly the same. So the plot with respect to position is the same for both the free particle as well as the propagator. And this makes sense. Why? See, the amplitudes of the plots are different as expected because this is an arbitrary choice, and in case of the free particle propagator, the amplitude is dependent on time. And but see, why the nature of the plots is same in this case? Because here we have chosen an arbitrary value of the amplitude a 0.5 for the wave function, and for the propagator the amplitude is under root m over 2 pi h bar t. So everything is constant here as well, m 2 pi h bar, and there is only a dependence on time. But when we are plotting with respect to position, we treat time as a constant. Even for the case of the propagator, we treat time as a constant, right? That's what we do. So that's the reason the time plays no role here, even though the amplitude of the free particle propagator plays, depends on time, but since we're plotting with as a function of position, we treat time as a constant. That's why it does not play any role, and that's why both the plots look the same, which is not surprising. Okay, but now if we plot as a function of time, we have already seen the plot of the real part of the free particle propagator as a function of time. But now let's generate a plot of the real part of the wave function as a function of time, and now we get this kind of plot. Here we see that there is a good difference between the two plots. You see, in both the plots with an increasing value of time, the wavelength is increasing, which makes sense because more time means less frequency, which means less energy, which means more wavelength, because energy and wavelength are inversely related, of course. So that makes sense. And but this decaying nature, which we can see in the propagator plot, cannot be seen in the wave function plot. This is simple because mathematically, of course, this is simple because in case of propagator, the amplitude depends on time, and you see it's inversely proportional to time, to the under root t. The amplitude is inversely proportional to under root t. So with time, of course, the amplitude should decrease, and we see the decaying nature. But here, for the free particle wave function, this is just independent of time. So of course, with time, we should not expect any variation, and there is no decaying or anything. And here there's a decaying. And physically, I have also told you how to understand this physically, because this time, whatever we write, this is actually a time interval, and for longer time intervals, the probability that the particle starting from A will exactly end up at B will decrease, and that is shown by this decaying nature. But you see, because the wave function by itself contains no information about the time evolution of the particle. To find out how the particle would evolve with time, we need to solve Schrodinger equation for the particle using the appropriate conditions. So by itself, since the psi does not contain any information of the time evolution, we do not see the decaying nature when we plot psi as a function of time. But we see this in the case of path integral. So all of this is nothing very much difficult. I mean, even by looking at the equation, you can see that of course this will be decaying if we plot with respect to time. But this interpretation, the way we are understanding and the way we are drawing the parallels between what role wave function plays in canonical quantum mechanics and what role the propagator plays in path integral, this is very important, because like I always say, like understanding two different formulations of the same theory, same physical theory, both are quantum mechanics, both give you the same results, both are quantum physics. Of course, under some circumstances, the path integral, using path integrals is more efficient, gives you better results. I mean, it's easier to use path integrals, for instance, in relativistic quantum mechanics, in quantum field theory. But at the end of the day, both are formulations of quantum mechanics. It's technically you can use path integrals to solve the problems that are usually much easier to do using Schrodinger's quantum mechanics. But and it might appear to you, what's the need of learning two different formulations of the same theory? But it's always a very good idea. I mean, not just a good idea, it's absolutely essential. If you are interested in research and all, it's absolutely essential to learn a theory in as many different ways as possible, because this not only asserts the logical coherence of mathematics. It's beautiful. See, we have learned all this stuff: Schrodinger's equation, de Broglie relation, E equals h2, using canonical quantum mechanics, so and standard quantum physics courses. Now, doesn't it, like, it's really beautiful, isn't it? Like, now we can arrive at the same results using path integrals, which is a very different formulation conceptually, mathematically, but it gives you the same physical results. So that's what I'm trying to say. Okay, and yeah. Finally, I would like to discuss with you something which is this thing. Now, there are many applications of path integrals. Okay, one of my personal experiences I would like to share with you is that initially I was very interested in quantum physics, quantum mechanics. Like initially, in the sense when I was in my the final years of my high school, and even in my undergraduate college, the first year of college, or maybe even up to second year of college, I was very much into, like, no, I will do formalism of quantum mechanics. I will do research in like fundamental physics, like hardcore theoretical physics, quantum mechanics and extensions like quantum field theory, beyond standard model physics, theoretical high energy physics, technically. And even today, I'm interested in all those areas, quantum gravity and all. Who is not interested? That sounds very much exciting. But the reality remains that that area of research is becoming very saturated, because there has been no significant breakthrough for the last few years, last few decades actually. And of course, funding is also very less in those areas. And at the end of the day, we all have to, like, think about our career as well, because none of us have an infinite source of money and income that we can just explore whatever we like. Number one. Number two, even if I, like, for a moment, if I stopped thinking about the funding, even then, that field is not really, like, that is interesting, but after a point of time, it feels like you're just doing mindless mathematics and all. But what is I mean, how does it really matter? I mean, it's not, it has no direct benefit to society. If I'm not saying that if your research has some benefit to society, you will get funding. That, of course, that is one important factor to consider. But even apart from that, look at nonlinear dynamics or biological physics, physics of complex systems. And this is a very active area of research, active matter physics and all, polymer physics. It's very interesting. Like, because you are using physics principles to study complex systems, study polymer segregation, DNA, how cell division happens. And this is also a very interesting question. Like, all of us, we began with a single cell, then the cell division began, and then differentiation. Differentiation means, I mean, how the cells of my brain and the cells of my heart and the cells of my kidney, they all have different functions. But how did this differentiation occur all by itself? And just from a single cell, this complex organism emerges. So all of this can be studied using physics. It's a very active area of research, and this also has very important applications in medicine, and many more. So that's what I'm saying. Anyway, now the point is, so initially I was very interested in quantum mechanics and this formulation of quantum mechanics and this kind of areas, and maybe that's why I chose the topic of path integrals for my undergraduate dissertation. Because you have to choose the topics when you're in your second year, even though this project was done in my final year, that is my third year. But the point is, so at some point, but now I am planning to pursue my master's, pursue my graduate degree in nonlinear dynamics and the physics of biological physics, or something along those lines. I mean, not hardcore technique, not hardcore formulation of quantum physics. So, but that doesn't mean that my learning path integrals was a waste of time. Even beyond giving me intellectual satisfaction, this was not a waste of time, because path integrals actually have very much applications in studying stochastic processes, and also in like stochastic process is a very important part of the physics of complex systems and statistical mechanics. So path integral has an important contributions there, and I am planning to I'm in the process of learning those. But right now I'm not very much aware about the applications of path integrals in statistical physics. But there are applications that I have seen, which is a good thing. Anyway, so finally in this for this video, the last topic that we'll be discussing is this thing, the free particle propagator and perturbation theory. So now let's consider a familiar scenario, a particle moving from space-time point A to space-time point B. Now this is also one very important question which is not usually explained in most path integral texts. Like in path integral we start mostly we always talk about the path from A to B, like the initial and the final states of the particle are fixed. But in quantum mechanics, owing to the uncertainty principle, you cannot fix the position of a particle at one point in time. But it's actually nothing is there is no clash of concepts, there is no paradox here. In path integral, what we're asking is, if the initial point of the particle is A, then what is the probability that it will reach a final point B? We are defining a particular final point arbitrarily, and we're asking what is the probability. As for the initial point, we are asking if the initial point is there. The initial point can vary, it is random, I understand, it is uncertain. But we're not saying that we know the particle is exactly at this initial point A, and no, that's not what we're saying. So anyway, so let us consider the familiar scenario, particle moving from space-time point A to space-time point B. We can break this journey from A to B in two parts by introducing an arbitrary intermediate space-time point C. Then according to, again, this is just the multiplicative law of propagators, already discussed, right? We have already discussed. This one. Yeah. An arbitrary intermediate point C. So the kernel from A to B is the kernel from A to C multiplied by the kernel from C to B and integrated over all possible values of xc, if you want to consider all the possible paths from A to B. So essentially we take all the paths from A to C and all the paths from C to B, and then we multiply, and then we do the same for all the possible values of C. Now that essentially is the same as taking all the possible paths from A to B, or this thing, kernel A to B. Now we initially fix the intermediate point C and sum over all paths from A to C given by the kernel KCA, and then sum over all paths from C to B given by KBC, and then we integrate over XC to take into account all possible values of the intermediate point C. This final expression is nothing but the sum over all paths from A to B given by kernel A to B. Yeah. Now the above equation is a logical result. Of course, this is a logical result. This does not, this will hold whether it's a free particle or a particle with a non-zero potential energy or whatever, it will hold. Now we have seen that finding the exact form of the kernel for particles with potential is very difficult. We already know. See, even we discussed so much about kernels or propagators for particles with potential and energies, linear potential, quadratic potential, but that was all under a lot of assumptions. We could not exactly derive, and even then it was so complicated, right? You saw just now. So in certain situations, we can use the free particle propagator in the above expression. In this expression, we can use in place of these kernels K, B, C, K, C, we can use the free particle kernels. Even though we are dealing with a particle whose potential is not zero, at least not zero through the entire length of the journey. Let me tell you what I actually mean by this. And this is a very basic idea of perturbation theory also, which is very important in modern physics. But again, I'll not be going deep into perturbation theory in this video, of course. So this approach is a cornerstone of perturbation theory. Now, when dealing with complex systems, it often becomes unfeasible or impossible to obtain an exact solution. In such situations, we can start with a simplified version of the original system, for which the solution is known or can be easily obtained. Then we introduce additional terms of increasing orders known as correction terms to this solution to account for the features of the original system that were ignored in the simplified picture. For instance, someone asks you, let me give you a simple example. What should I say? You can think of it like this. Someone asks, suppose you go to I don't know. You go to rent an apartment suppose you are moving to a different city for your studies or different country, maybe, whatever. and you rent an apartment, student accommodation, and then you ask what will be my average monthly living expenses. They give you a rough amount. It will be, I don't know, maybe say $100 per month, very rough amount. So this is a gross amount. Like suppose you are like booking your accommodation now, or even though you'll be moving in after 3 months maybe, or maybe after 4 months. But you are booking the accommodation now because the accommodations gets filled up. Accommodations get filled up very fast. So at this time, you can ask the homeowner, you can ask the the landlord, like, can you give me a rough estimate of what will be my monthly expenses, because I need to plan my finance, plan my budget accordingly. So he may tell that, okay, you'll be needing $100 per month. This is a gross estimate. So in terms of perturbation theory, this is the zeroth order correction. Like we start with this very simple very simple case. Okay, $100. But once you reach there and once you start living, you will understand that no, it's not exactly 100. Maybe the $100 was just your room rent, but you have to also consider the money you need for your Wi-Fi connection, the money you need for your electricity bills, and maybe your own expenses. Maybe you go out or you have some food or whatever. So considering all of that, maybe you calculate that the monthly expense is actually $110, suppose. So that means you can write 110 as 100 plus 10. So this plus 10 is actually a correction term. So you started with a very simple picture, $100 gross estimate. So you can plan your finance, plan your budget accordingly. But once you reach there, you have 100. You see that no, it's actually turning out to be 110. So this extra 10 is your correction term, first order correction, 100 plus 10. Now after 5 months, suppose after living there for 3 months or 4 months or 5 months, whatever, you become a pro at managing your budget, your finances. So you can cut down on unnecessary costs. Then you see that, oh my god, I can actually manage it in $105. I don't need 110. So then what you will say? You will say, okay, so my expression is 100 plus 10 minus 5. So now you are able to cut minus $5 from your monthly expenses. So now the total is 105. So this is your second order correction. So now this is just a very like rough idea, but I think you'll be able to understand it more better in the context of physics, the idea of perturbation theory. So when dealing with complex systems, it often becomes unfeasible or impossible to obtain an exact solution. In such situations, we can start with a simplified version of the original system for which the solution is known or can be obtained. We then introduce additional terms of increasing orders known as correction terms to this solution to account for the features of the original system that were ignored in the simplified picture. Like in the first simplified picture, in the first term of the zeroth order correction, some complex features were ignored just to keep things simple. But then we add correction terms so that our result is more and more accurate to the original result. See, if we try to study a complex system, if we directly try to solve the equation for the system as it is, that will give us the best, most accurate result. But that is not possible always. Sometimes that is very difficult, even computers cannot handle, and sometimes it's downright impossible. So what we do is, we start with the simplified version that we can handle, and then we add correction terms. Now the more and more correction terms we add, as we go to higher and higher order correction terms, our solution is very much close to the actual accurate solution. So we're following a longer path, but a path that we can take. It's not impossible. That's the philosophy of perturbation theory. Why it's called perturbation? Because we are like subjecting the system to small disturbance, not small perturbation, to get the actual system. We start with a very simple unperturbed system, and then we adding correction terms means adding perturbations, kind of. Okay. So essentially, we introduce small corrections or perturbations to the initial solution to obtain a solution that describes the original system with a reasonable degree of accuracy. This is what perturbation theory is basically about. And although this approach might appear messy, it's extremely useful in many areas of physics and mathematics. So although a detailed discussion of perturbation theory is not possible, we will look at an interesting scenario. This is kind of, you can say, an example of perturbation theory approach as well as a kind of an application of path integrals. That's why I'm discussing this. We aim to calculate the probability amplitude of a particle moving from point A to B. So far so good. Now this is not a free particle. So if we assume that the particle is initially free particle, that it has no potential energy from A to B, from A to C, and as well as from C to B. But it experiences us. I'll go to that later. First of all, first is the zeroth order approximation. First, we assume that the particle has no potential energy, it's free. So, first of all, we're assuming that the particle is a free particle. From A to B, for the entire length of the journey from A to B, the particle is a free particle. So, this is the zeroth order approximation, the simplest possible scenario. And in this case, of course, in this expression, we can use the free particle propagator. So, we can write K0BA as the integration dxc, K0BC, K0CA. Very good. Zeroth order approximation. Now let us assume, now this is the first order approximation. First order approximation means we will introduce a little bit of more complexity, little bit of perturbation in the system. So now we will assume that the particle momentarily experiences a non-zero potential at the intermediate point C, although it moves freely from A to C and from C to B. So this is the first order approximation. I mean, this is what I mean. From A to C, the particle moves freely. It's a free particle. But at the point C, for a very small period of time, like for a very infinitesimally small amount of time, momentarily, the particle experiences a non-zero potential. So when the particle is at C, then you cannot say that it's a free particle. Then again from C to B, it's a free particle. So it's more or less a free particle except for this point in between. So this is a first order approximation. It's a first order correction. You are introducing correction. Now, as we already know that calculating the kernel at point C, you can say, okay, so the particle is not a free particle at point C. That means we have to calculate the kernel for the particle at point C. The kernel means the kernel for a particle with a non-zero potential. But we've already seen that calculating the propagator or kernel for a particle with non-zero potential is very, very complicated. So you need not do that. You can still use the free particle propagator, which is very much simple to deal with, even in this case, under perturbation theory, under the first order approximation. What you can do is that, in this case, you can write that, first of all, you use the free particle propagators. K0, from A to C, use the free particle propagator. From B to C, also use the free particle propagator. But you multiply with Vc, because Vc is nothing. Vc is this, the potential at C. So, at the point C, the particle momentarily experiences potential, and that is Vc. So, you multiply with Vc. And then you integrate over dx or dxc, all the possible values of xc, minus infinity to plus infinity. And you also integrate over dtc. From TA to TB. TA to TB is from the initial time A to the final time B, and you integrate over dTC over the time variable TC. Why? Because this, you need to bring this into picture, because right now there is an element of time, because right now the particle, I mean the potential is varying with time. At the point C, the potential is constant Vc. But if you look at the particle, I mean if you think from the point of view of the particle, from the reference frame of the particle, then the potential is zero for this amount of time. But when the particle is at C, I mean at time t equals to Tc, the potential is suddenly non-zero. Then again the potential is zero. So overall there is a variation of potential of the particle with time, and that's why you need to integrate with time as well. With time in the sense with all possible values of Tc, but for the limits at Ta to Tb. And why minus 1 over h bar? See, this is, I cannot show you the exact kind of mathematical derivation, but you can think of it like this. In the expression for the action, what we have in the action S was what? A time integral. Action S was time integral L dt, Lagrangian dt, and Lagrangian was kinetic minus potential energy. So before the potential energy there was a minus sign, L minus T minus V. Lagrangian L was T minus V. So action was what? Time integral T minus V. I mean, so if you consider only the potential energy right now, because yeah, so it will be minus V dt. So time integral, see we have a time integral minus, we have a minus here, and we have a V, and we have a dt, and 1 over h bar, because what was this contribution? I mean, what was the kind of, like in the expression for the kernel, what did you write? We wrote e to the I s over h bar, e to the I into action s over h bar. So that basically exponential to the power 1, inside the exponential we have I over h bar into the action. So we have a I over h bar here, and from the action we have a negative and the potential energy and the time integration. So this extra time, it is coming because of this momentary potential. Otherwise, see, it's just integration dxc, k0bc and k0ca, just this, nothing more. Okay, so I think you get this expression. So this is a very good approximation. Although you don't have to actually calculate the propagator of the particle considering the potential. You are using the free particle propagator expressions here and here to keep things simple. You are just introducing some little corrections in the expression, and this will give you a very good approximation of the kernel from A to B. In this case, when the particle when the particle momentarily experiences a non-zero potential at C. Okay. This is the point. This is what I was trying to convey. And I mean, Yeah, you can we can extend this method further. See, in a second order approximation, the particle experiences non-zero potential for two intermediate points. So if you talk about the second order approximation, then you take a point C where the particle experiences the momentary potential Vc. You also consider a point D, intermediate point D, such that D is greater than C. I mean, TD is greater than TC, because the particle is at point D after the particle is at point C. So that's why I've written, you see, I've written TD greater than TC. Because if I don't write this, then the particle can violate causality, because the particle first comes at point C and then then goes to point D. Yeah, as for the space, as for the position, we cannot say anything, because it's like, you see, this is XC and this is XD. So XD is actually less than XC. The particle can move either to the left or to the right. I mean, in one dimension, the particle, from the point of a position, the particle can take positive or negative direction. It can move both ways. So no problem there. But from the time, on the time scale, D is greater than C. So yeah, in the second order approximation, we take two intermediate points C and D, where the particle experiences the momentary non-zero potentials Vc and Vd respectively. So from A to C, the particle is a free particle. Here the particle momentarily experiences Vc and then goes to, and then from C to D it again is a free particle. Then at point D it experiences a momentary potential Vd. Then from D to B it's again a free particle. So this is the second order approximation, and we can keep on doing this for even higher order approximation. Now the point is, if you take a very high order approximation, maybe 100th order approximation or something, then essentially using this method you can actually describe a particle which is not a free particle at all. I mean, it's more or less, it has some potential throughout the entire journey, because you are taking 100 intermediate points or something, if you talk about the 100th order correction. So that means you can essentially describe a particle which is not a free particle at all using the free particle propagators. And this, I don't know if I have been able to impress this upon you, but this actually is a very good a great simplification, because calculating the kernels for particles with non-zero potential is very much complicated mathematically. And yeah, this case which we're considering, this actually has a very good physical application, I mean physical analogy as well. You must have heard of this scattering experiments, the most common of which, I'm sure you have heard of it, even in high school we learn about it. It's Rutherford's alpha particle scattering experiments. So, or in any kind of experiment, suppose you are firing a particle towards maybe a metal gold foil or something or whatever. You are firing a particle towards some atoms, like in Rutherford alpha particle scattering experiments, those metal atoms, right? So suppose from the initial position of the particle, from the position where you are firing the particle, and up to when the particle reaches the metal or reaches the atoms, the particle is more or less a free particle, right? So suppose you are firing particles towards a target. So from here to the target, the particle is a free particle. But once the particle reaches the target, it experiences the potential. For instance, in case of the alpha particle scattering experiment or electron scattering experiments, once the particle reaches the vicinity of the atoms, the metal atoms in the gold foil or whatever, in many more cases, alpha particle is only one example. So once the particle reaches close to reaches the vicinity of the nucleus of the atoms, the particle gets deflected, right? Some particles may get deflected, some particles rebound back, and using this we can study the structure of the nucleus, right? So like you see here, the particle is moving out, and at point C the particle momentarily experiences the potential, which you can think of it in our discussion right now in the context of scattering experiments. You can think of it as the potential of the nucleus, the Coulomb potential of the nucleus of the target atoms, and experiencing the potential momentarily, the particle is deflected. So that's what I've written here. You see, the higher the order more accurately we can describe a particle that has some potential energy using the free particle propagator. From here you see, a physical application of the above method is the scattering of electrons on hitting a thin metal foil due to interaction with the metal atoms. It's often of interest to find the probabilities of finding electrons at specific angles with the original direction after the scattering. I mean, of course we ask the question like, what percentage of electrons are scattered by what angle, what's the distribution, right? And using this knowledge we can study the structure of atoms, nucleus, and so on and so forth. That's why we do scattering experiments, to study the internal structure. Even in more exotic, like high energy physics experiments, particle colliders and all, this is what we usually do, right? We studying of scattering cross section, scattering phenomena, scattering amplitude is very, very important. Now the probability amplitude of the propagator can be calculated using the above method, and by taking the square of the modulus of the propagator, the probability of finding the electron at a particular angle can be calculated. So the potential at the point of interaction between the electron and the metal atoms is the electron's Coulombic potential energy when it's in the vicinity of the electron of the metal atom. Just what I said. Yeah. Okay. So yes, I think that's it. Nothing more I would like to discuss for this video. Anyway, it's a very long video already. So I think now combined with the previous video, I think I gave you a very good introduction to path integrals for a layman level, for undergraduate level. So yeah, I hope you found the video insightful and useful if you are into studying these kind of things, or if you are studying whatever. I would like to know of your feedbacks in the comments, please. And yeah, thank you for watching. If I managed to watch the video till the very end, thank you for watching.